अच्छा बोलिए।
Good morning to one and all present here. I, Dhruv Singh,
and I, Vishruta Tyagarajan,
on behalf of VIT Bhopal University, welcome you all to the International Conference on Sustainable Aerospace Technologies and Innovation, ICSATI 2025. We are honored to have the presence of all of you on this auspicious occasion. As we come together today for this important event, we ask the Almighty to shower us with divine wisdom and insight to guide the discussion and deliberation held throughout the conference.
Now, we request everyone to stand for the Tamil Thai Varthal. Now we invite the dignitaries on the stage. We invite our Vice President, Mr. Shankar Vishwanathan, our Chief Guest, Dr. Ajay Kumar Rai, Dean of School of Mechanical Engineering, Dr. S. Balaguru, Dean of Faculty Affairs, Dr. Devashish Adhikari, our Conference Chair, Dr. Prashant G.K., Conference Chair, Professor Suresh Sampath Sir, our Pro Vice Chancellor, Dr. T.B. Sridharan, Shubham Karoti Kalyanam, Arogyam Dhanasampada, Shatru Buddhi Vinashaya, Deepa Jyotir Namostate. The lighting of lamps has been a divine ritual among us. It symbolizes the ignition of hope in our hearts and fills us with courage to make the legends, the victory of good over evil, hope over despair, and virtue prevailing over vice, true. So, we would like to invite our dignitaries to light the lamp and lay the cornerstone of our conference.
Now, I would like to call the Dean of School of Mechanical Engineering, Dr. S. Balaguru sir, to deliver the welcome address.
Respected Vice President Mr. Shankar Viswanathan sir, esteemed Chief Guest of today's function, Dr. Ajay Kumar Ray, Director, JS Institute of Advanced Studies and Research, and also the former Professor of IIT Kharagpur, respected Pro Vice Chancellor, Dr. T.B. Sridharan sir, Dean Faculty Affairs, Dr. Debashish Adhikari, Conference Chair, Dr. Prashant GK, and also International Advisory Board President, and also the Conference Chair, Dr. Suresh Sampath, Professor, Cranfield University, Organizing Secretary of this conference, Dr. Ankush D. Tarkar, Co-Organizing Secretary, Dr. Vijay Kumar Patidar, other IAAB members and delegates from various countries, deans and directors, participants from various colleges, my dear students, good morning to all. It gives me immense pleasure for me to welcome you all to the first edition of ICSATI conference. ICSATI stands for International Conference on Aerospace Sustainable Technologies and Innovations. It is the first conference being organized by the Aerospace program of School of Mechanical Engineering, and incidentally the fourth conference for the School of Mechanical Engineering under my deanship. Before I go for my welcome address, I would like to share some of the salient points of the Aerospace Engineering program with the chief guest, Dr. Ajay Kumar Ray. Among 4 campuses of VIT Bhopal is the only campus which offers the Aerospace Engineering program. This is a flagship program under the School of Mechanical Engineering. We receive top-notch students from across the country for this program. Yesterday, we had a pre-conference workshop on gas turbine technology. The workshop was delivered by the conference chair and also the IAAB president, Dr. Suresh Sampath, Professor, Cranfield University, and Professor Nicholas of University of Patras, Greece. Both the resource persons were very much satisfied with the participation and involvement of our students. So far, 2 batches from Aerospace Engineering have passed out. In both the batches, more than 40% of the students went for higher studies abroad, and all the students, remaining students, were placed. We have International Aerospace Advisory Board headed by Professor Suresh Sampath sir as the president. The board consists of 8 members. All the 8 members are the reputed persons in the field of aerospace engineering from across the world. Moreover, VIT Bhopal University is recognized as the bronze medal sponsor at the ISAB conference, International Society for Air Breathing Engine Conference, held in France in September 2024. Now, I formally go for my welcome address. First of all, I would like to welcome our respected Vice President, Mr. Shankar Viswanathan sir. He is a person known for his simplicity. Under the visionary leadership of our top management, our institution has grown by leaps and bounds for the past 7 years and is poised to grow further and further for the years to come. Though it is a welcome address, I would like to thank our Honorable Chancellor, Dr. G. Viswanathan sir, Vice President Shankar Viswanathan sir, Assistant Vice President Ms. Kadambari S. Viswanathan ma'am, and our trustee ma'am for their encouragement and support in organizing this conference. Sir, we are happy to have you with us today. I welcome you, sir. I welcome our esteemed chief guest, Dr. Ajay Kumar Ray, Director, JS Institute of Advanced Studies and Research. He is a former professor of IIT Kharagpur and a former director of IIEST Shipur. Professor Ajay Kumar Ray belongs to Electronics and Communication Department of IIT Kharagpur. He carried out an extensive research in the field of avionics. Avionics requires the application of electronics in the field of aerospace. And he is a Padma Shri awardee. We are happy to have you as our chief guest. I welcome you, sir. I would like to welcome our respected Pro Vice Chancellor, Dr. T.B. Sridharan, sir. He is very simple and good at extracting work from employees without affecting the morale. Incidentally, this is the first conference under his leadership at VIT Bhopal. I welcome you, sir. I welcome Dean Faculty Affairs and General Admin Dr. Debashish Adhikari, who leaves no stones unturned. I welcome you, sir. I welcome International Aerospace Advisory Board President Dr. Suresh Sampath, Professor Cranfield University. He is a doyen in the field of gas turbine technology. He worked for Indian Navy for about 22 years. I welcome Dr. Theocles Nicholas, Associate Professor, University of Patras, Greece. Incidentally, both Dr. Suresh Sampath sir and Theocles Nicholas obtained their Masters and PhD from Cranfield University. Dr. Suresh Sampath sir worked for Indian Navy for about 22 years. Dr. Theocles worked for Greek Aerospace for 20 years before taking over as the professor at University of Patras, Greece. I welcome both Dr. Suresh Sampath sir and Theocles Nicholas sir. Whenever we think of a luxury car, the first and foremost car which comes to our mind is Rolls-Royce. It is a epitome of luxury. So other luxury cars will work for 15 years and they become obsolete. But Rolls-Royce car will work even for 100 years. We are happy to welcome the president of Rolls-Royce South Asia, Dr. Kishore Jayaraman, sir. Recently, he has taken over as the chairman of UK India Business Council. I welcome you, sir. I welcome our other IAAB members, Dr. A.M. Pradeep, Professor and Head Aerospace Engineering Department, IIT Bombay. I extend my warm welcome to our other keynote speakers, Dr. V. Ashok, Outstanding Scientist and Associate Director, Vikram Sarabhai Space Center, Dr. A. Muniyappan, Deputy General Manager, Tata Advanced Systems Limited, Dr. Sudhir Joshi, Professor and Head Aerospace Engineering, Graphic Era deemed to be University, Dr. T.K. Sundaramurthy, former Mission Director, ISRO, Dr. Ravi Kumar Verma, Scientist, Space Application Center, ISRO. I welcome Dr. Srinivasan, Director, International Affairs from VIT Vellore, and I also welcome other faculty members from our VIT campuses. I extend my warm welcome to other two members who are joining online for keynote, Dr. Frank, ISAB President and Senior Vice President Airbus, and Dr. Simi Gergis, Associate Professor, Pratt Whitney, and Canada. So, dear students, before I conclude my speech, I want to make this point clear. Today and tomorrow, you are going to have eminent persons in the field of aerospace from across the world in our campus. This is the rarest opportunity for others. You are bestowed with this opportunity. I request all the students to make use of this opportunity and flourish. Thank you.
Thank you, sir, for giving this conference an enthusiastic start.
Now, I would like to call upon the Pro Vice Chancellor of VIT Bhopal, Dr. T.B. Sridharan, to deliver the welcome address for the gathering.
A very good morning to one and all present here. It's my immense pleasure to invite our Honorable Vice President, sir, Sri Shankar G. Vishwanathan, sir. Hearty welcome to you, sir. I invite Professor Ajay Kumar Ray, Padma Shri awardee, as a chief guest of this conference. Sir, I warmly welcome you on behalf of VIT Bhopal University, sir. Warm welcome to you, sir. I also welcome Professor Suresh Sampath, sir, a very eminent aerospace scientist from Cranfield University, UK. I warmly welcome you on behalf of VIT Bhopal University, sir. I also welcome Professor Debashish, sir, Professor Balaguru, sir, for almost a key role in this organizing this conference. Also, Professor Prashant, who is the organizer of this conference. I also welcome eminent guest Dr. Kishore Jayaraman sir, Rolls-Royce President. We are really happy to see you, sir. Very rarely we see that Rolls-Royce car, maybe one or two recorded in Tamil Nadu, I'm not sure. And now we are seeing him in person. We are really very proud and very happy to receive you here, sir. I warmly welcome on behalf of VAT, Babal University, sir. I warmly welcome Professor Ashok, sir, Professor Theocles, Professor Pandian, sir, Professor Muniappan, sir, and many more dignitaries or from ISRO, IITs, and all. I also invite our deans and directors of VT Babal University. I also invite the delegates from VT Vellore and other universities, students, research scholars, press, media. A very warm welcome to you all for this occasion of first International Conference on Sustainable Aerospace Technologies and Innovations 2025. So this conference is organized with hybrid mode. One external guest is also coming to speak to you in online mode as well. Before going to the conference, I would like to just see the past history of aerospace. In the beginning, birds only occupied the space, and we learned from bird and started to willing to fly, but it is just impossible. We cannot fly, so we use crafts. The very famous invention of humankind done by Wright brothers, who discovered aeroplane. Not only it's a simple discovery, it changes the entire human life, entirely totally different into a new revolution. Really, it is a memorable and wonderful discovery. Since then, today, we can see fastest vehicle on the earth is only done by aerospace technology. So, such a wonderful the research area, as well as very futuristic values, very high values. Second point I would like to quote: in the ancient times, the commerce business, export imports are too high, and people used to export or import goods from other countries, other continents. And there is a famous quote: all the material has to come through the ship and export or import for the same. There is a famous quote: one who rules the sea ruled the earth. I repeat again: one who ruled the sea ruled the earth. That statement was widely accepted across the globe at that time. But today, if you see, the phrase can be rephrased: one who dominates the space will rule the earth. That's my opinion I would like to share. So on that basis, this conference has been organized by the Department of Mechanical Engineering and in collaboration with many other leading primary institutions of India and abroad. This conference focuses on many specific areas like aerodynamics, astrobiology, astrophysics, space robotics, space applications, sustainable technologies, metallurgy. Initially, Wright brothers used wood, muslin cloth, and other things to construct the plane. But metallurgy and other research on speed engines made them a revolution. I understand, if I'm right, the fastest vehicle travels 5,000 kilometers by some aircraft, which I'm not very sure about it, but name I'm not sure, but I understand it's correct. So many research areas are sustained in this field of aerospace technology, which makes the global very small. In few hours, we can reach one end to other end of the globe. So the global village the term applies. And the aerospace technology and research reaches the sky. And I would like the conference echo should reach the sky and come back to us and all over the globe. It's my immense pleasure to invite you all dignitaries on the dais, scholars, students, every one of you, to make utilize of this extremely valuable conference. And I wish all the success. Thank you.
Thank you, sir, for your very thoughtful insights.
Today, we are honored to have the presence of our chief guest, Padma Shri Awardee Dr. Ajoy Kumar Rai, Director, GIS Institute of Advanced Studies and Research, former Professor of Electronics and Communication Engineering at IIT Kharagpur, former Vice Chancellor of Bengal Electronics and Science University, Shibpur, now IIEST Shibpur, is an alumnus of Bengal Engineering College. Dr. Rai earned his MTech and PhD from IIT Kharagpur, where he later joined as faculty in 1980. He has led 20 plus research projects funded by agencies like DRDO, DAE, DST, INDL, and Intel Corporation, co-inventing six US patent with Intel and 5 US patent with Texas Instrument. Dr. Ray has published 160 plus research papers and authorized 5 books, including one in Chinese, with leading publishers like John Wiley, Tata McGraw-Hill, Prentice Hall, and Kellner Francis. He has served as community research fellow at community university academic bodies and as chairman and secretary of Nehru Museum of Science and Technology, IIT Kharagpur. Now we request our vice president to felicitate Dr. Ajay Kumar Rai with a bouquet and memento as a token of our love and respect.
Now, we kindly request our conference chair, Dr. Prashant GK, to throw some light on the conference.
Respected Chancellor, Vice President Sir, Assistant Vice President Ma'am, Trustee Ma'am, Pro Vice Chancellor, esteemed dignitaries, deans, program chairs, distinguished speakers, faculty members, and dear participants. It is with immense pride and honor that I welcome you all to the International Conference on Sustainable Aerospace Technologies and Innovations 2025, organized in association with International Society for Air-Breathing Engines, ISAB. International Society, ISAB has been a part and an integral part of the conference, and Professor Suresh Sampath has been the leading guide to the association with this conference. ISAT 25 is a celebration of cutting-edge research, technologies, achievements, and advancements and global collaborations in the aerospace sector. This conference has been meticulously designed to serve a platform where academia, industry, and research organizations converge to explore sustainable solutions in the future of aerospace technology. This year, ISAT 25 has seen overwhelming participation from across the globe. We received an impressive 352 research contributions from various prestigious institutes. Out of these, a rigorous peer review process, 51 papers have been accepted and maintaining an acceptance ratio of about 15%. This ensures that only high quality publications, innovations, research is presented at this esteemed gathering. We are proud to have this received contribution from 4 different countries, alongside significant participation from premier national institutes, including IITs, DRDO, BSSC, ISRO, IIEST, and several other leading universities. The conference features a diverse and engaging agenda, including 9 keynote sessions by globally renowned experts, 2 panel discussions addressing the most pressing challenges and future prospects in the aerospace technologies, poster presentations and technical sessions showcasing groundbreaking research, a student competition aimed at fostering innovation and among young minds, cultural events to celebrate the vibrant spirit of academia and collaboration. We are deeply grateful to the generous support that we have received from DST, Department of Science and Technology, and further support by key industry partners like Dr. Aerospace and Jet Aerospace and the Institution of Engineers. Their belief in this initiative have played a pivotal role in making ICSATI 2025 a reality. This conference has been backed according to the powerhouse that is the VIT management. To recognize outstanding contributions, we are delighted to present the Dr. APJ Abdul Kalam International Foundation Best Paper Award, Dr. G. Vishwanathan Best Poster Award, technical awards in multiple categories. Our pre-conference engagements have also been remarkable, with over 120 participants registering way ahead of time. As a conference dedicated to sustainability, our conference kits reflect our commitment to environmental responsibility too. We are providing with the jute bag, a notepad, a pen, conference badge, followed by the souvenir and a sapling to step forward a greener tomorrow. What makes ICSATI 2025 truly special is that everything right from planning to execution has been organized entirely by a dedicated team of the students, the faculty colleagues and mentors. Their tireless efforts, passion, and teamwork have shaped this conference into an extraordinary platform for knowledge exchange. Finally, we are proud to announce that selected papers of the ICSATI 2025 will be published in the Springer Lecture Notes in Mechanical Engineering, further amplifying the research and impact of the research presented here. With that, I extend my heartfelt gratitude to each and one of you being part of this remarkable journey. May this conference ignite new ideas, foster collaborations, and pave the way for a more sustainable and innovation future in aerospace technology. Thank you.
Thank you, sir, for such detailed information.
The souvenir of this conference stand as a testament to wealth of the knowledge, groundbreaking research, and collaborative spirit that define this prestigious conference, serving as a cherished reminder of our shared commitment to innovation and progress. It is with immense pride and joy that we invite our chief guest to release the ICSA TI 2025 souvenir.
This souvenir captures the essence of this momentous event and the collaborative efforts that make this conference a remarkable gathering of minds. We now invite our chief guest, Dr. Ajoy Kumar Rai, to please grace us with your warm words.
A very good morning to all the students, research scholars, very distinguished members of eminent club of researchers in aerospace engineering from across the world. And most importantly, the management of VIT, who have made such momentous occasion a reality. I'm indeed extremely happy to be here on this great occasion with you all. And as we just knew from the report of the Vice President, it's really remarkable that VIT and VIT Bhopal University has made tremendous strides in so many branches of education in science and technology in such a short time. So the credit goes to the faculty members, the credit goes to the researchers, to the management, and most importantly to all of you, the students who are there to enhance the prestige of this great university. I am further delighted to see that the topic of this conference is on sustainable aerospace technologies. Usually, taking care of this very important, small yet significant term, sustainability, in all aspects of a particular discipline is very rare. As you all know that the whole world is on the brink of a major disaster, and after Paris Agreement, all the heads of the states, including the head of United States, they all have agreed that, okay, we must cut down the release of greenhouse gases. The major problem today that stands is this aeronautics and aerospace area. It is one of the major contributors of greenhouse gases. Almost 2.5 to 3% of the total greenhouse gases which are being emitted is from this sector. So naturally, the question that comes is how to tackle the problems. There are problems and there are solutions, because humanity has always strived for looking for the solutions, and the estimation is that by 2050, the entire aeronautics and aerospace industry all over the globe will be zero carbon industry. So that's a great thing, and that can be possible only by you, the very eminent experts, specialists, and our young research scholars and students who are in this area to do it. The first thing that comes is obviously, as Dr. Shampat was mentioning, that Professor Siddharth was mentioning that it's very important to understand the utility of this sector, because the total number of the air carrier users is going to almost double in no time. So what will happen? One of the predictions is there may be even about 100 billion passengers in 2050 all across the world. This is very highly exaggerated estimate. But then even if it comes to a small part of it, that's really quite alarming. So we need more aircrafts. We need the aircrafts to consume less energy. And consumption of less energy does not mean that only in the propulsion you make the changes. It means that we must look at the entire space of aerospace engineering, starting from manufacturing of aircrafts. Then the propulsion is a very important thing. The structural part, I found that there are a lot of very eminent speakers who will be talking about the aerodynamics, and students, please attend all these lectures very carefully. There are problems on propulsion. It is extremely important that we must go for alternate propulsion. Although people are talking about almost, now hybrid, that is electric propulsion is coming. Hydrogen is a very important area. Usually, I spend quite a lot of time in USA these days after my retirement for at least 3 to 4 months. And I found that so many places, so much of work is being done. The government is also spending a huge amount of money in America, in Europe. In our country, the amount which is spent may not be that high, but then the government also has been trying to give as much support as possible to do research in this area. Hydrogen may be a very important area, not only in the aircraft industry, but elsewhere as well. Material science. So the aerospace engineering, remember, my dear students, is a very much, interdisciplinary area. You need, on the one hand, how to design the aircraft, how to take care, you must know very well the finite element models, how to take care of the diverse atmospheric situations, and many other situations in aerospace industries. So it's interesting that you must be quite aware of the diverse aspects of it. You need mathematics, you need to know Navier-Stokes equations, highly nonlinear, multidimensional systems. And to compute them, you need very high-speed computing. Where do you get it? Because after all, a very important aspect which is coming out is the application of AI in almost all the sectors. Even in the design of propulsion, also you have to take care of the AIs. So AI is coming in a big way. For doing good research, you need huge amount of data. Data collection is one thing. I heard yesterday that you have got here one IoT and robotics center also in this university. That's really very commendable. Now, what you need to do is that you need to do a lot of research on drones. Young students, they are very much fascinated with robotics and drones. Just keep on doing it, but always keep it in mind. Now, whatever you do, even if a simple quadcopter drone, even if you design, please take care of one thing, that it must be sustainable. What is the amount of energy you are spending right from the manufacturing stage to the operational stage. Everywhere, the total amount of energy consumption must be kept in mind. And one of the important things is to make them lighter. So naturally, you need to do lots of research in the area of material science. Titanium has been for a long time has been used. Now titanium being, added with molybdenum, a very important area of research altogether is coming up. That is how the different alloys of titanium with other metals can really lead to the material, which will be the material for the future aerospace or aircraft or the carriers. Interesting thing. And in a university like, VIT Bhopal, I'm sure that you will be doing wonders. My dear students, please take up, since I was very happy to know from Professor, from Professor Sridharan, that there are so many different schools where the students are working till the late hours in the night. And here also Professor Pradeep was mentioning to me, the Dean mentioned about the huge amount of effort that you have been giving. So please do something, make some prototypes. Remember that only making a prototype will not do. You must know how to do simulations. For that you need to compute. And you need to, don't use only ChatGPT and don't think that that is the end of life. Because use generative AI quite extensively, but use it with your thoughts. Use AI with your conscience. Remember that there's a lot to learn and a lot to think. Keep on asking questions that why this, why not that? And as he was mentioning, that we learn from the birds to move, fly, and even from these natural sector, the animals, the birds, the insects, we still have a lot of things to replicate. A huge, a completely different engineering has been coming up, which is nature-inspired, bio-inspired engineering. Lots of things you can simply mimic the way you are doing here. American Air Force, they found that, okay, even their fighters and bombers, when they are moving, making so much of noise. But have you just seen that the flocks of birds, which when they move, absolutely they do not make any noise. Why? And then, what is the mechanism of their flight path? Even here, see, the engineering means it's human thinking, human creativity. People have thought that, okay, there are certain things, many people, they feel that, okay, only greenhouse gas is carbon dioxide. But then now it is being found that the nitrogen oxides, which are also being released, that creates a major problem. That means that creating those white trails which are coming from the jet engine, how to take care of that? There are so many different aspects. So take care of different aspects. Different students can take up projects in different areas and keep it up. And remember that one day people should say that this institute, the Vellore Institute of Technology, Bhopal campus, they are the best in this area. And they have done lots of indigenous projects. And I convey all my blessings, my best wishes to each one of you for a glorious, peaceful, harmonious, and then a very innovative future in the days to come. Thank you.
Thank you very much, sir, for your inspiring words. Now, we request our Vice President, Mr. Shankar Viswanathan, to felicitate our chief guest, Professor Ajay Kumar Ray. Now, we request our Dean Faculty Affairs, Dr. Devasis Adhikari, to deliver the vote of thanks, extending our heartfelt gratitude to all those present here and to those who have contributed to the success of this event and supported in making this gathering possible.
Honorable Chancellor, sir, respected Vice President, sir, respected Assistant Vice President, ma'am, respected Trustee, madam, esteemed dignitaries, respected Pro Vice Chancellor, distinguished guests, faculty members, and dear participants. It is indeed an honor and privilege for me to extend the vote of thanks on this prestigious occasion of the International Conference on Sustainable Aerospace Technology and Innovation, ICS-ATI 2025. At the outset, I would like to express my heartfelt gratitude to our chief guest, Professor Ajay Kumar Ray, Padma Shri Awardee, Director, JIS Institute of Advanced Studies and Research, former Director, IIEST Shibpur, former Professor, IIT Kharagpur, for gracing this event with his esteemed presence. Sir, your inspiring words and invaluable insights have set the perfect tone to this conference. We are immensely grateful to our distinguished speakers and eminent dignitaries who have joined us today to share their expertise. Dr. Frank Hasselbeck, President ISAB and Senior Vice President Airbus. Dr. Sami Girgis, Associate Director, Pratt & Whitney, Canada. Dr. Suresh Sampath, Head, Gas Turbine Systems Engineering and Operations Group, Cranfield University. Dr. Theoclis Nicolaides, Associate Professor, University of Patras, Greece. Dr. Kishore Jayaraman, OB, Chairman, UKI BC, India, and former President, Rolls-Royce, India. Dr. Ashok V, Outstanding Scientist and Associate Director, VSSC. Dr. Muniappan A, Deputy General Manager, Tata Advanced Systems Limited. Dr. A.M. Pradeep, Professor and Head, Aerospace Engineering, IIT Bombay. Dr. Sudhir Joshi, Professor and Head, Aerospace Engineering, Graphicera, deemed to be University. Dr. T.K. Sundaramurthy, former Mission Director, ISRO. Shri Ravi Kumar Verma, Scientist, Engineer, SF, Space Application Center, ISRO. Your presence and valuable contributions have elevated this event, fostering discussions that will drive innovations in aerospace technologies. A special word of appreciation to Professor Srinivasan, Director International Affairs, and all the esteemed delegates from IITs, NITs, VIT, DRDO, VSSC, ISRO, and other premier institutes for their participation and collaboration in making this conference a grand success. I extend my deepest gratitude to our Honorable Chancellor, Vice President Sir, Assistant Vice President Ma'am, and Trustee Madam for their continuous support and vision and encouragement in making this conference a reality. A sincere thanks to the organizing committee, faculty members, and volunteers who have worked tirelessly behind the scenes to ensure the seamless execution of this event. Your dedication and teamwork are truly commendable. Lastly, I would like to thank all the attendees, researchers, and students for your active participation and enthusiasm. Your presence and engagements make such events truly meaningful. With that, I once again express my heartfelt appreciation to everyone who contributed to the success of this conference. Thank you all, and I wish you with enriching discussions and fruitful collaborations ahead. Jai Hind.
We now request our Vice President, Mr. Shankar Vishwanathan, to felicitate our dignitaries, starting with Mr. Suresh Sampath, sir. Dr. Suresh Sampath. Professor Theophilus Nicolaides. Dr. Kishore Jayaraman. Dr. Sudhir Joshi. Dr. V. Ashok. Shri Ravi Kumar Verma. Dr. Muniappa Ne. Professor A. M. Pradeep. Dr. Srinivasan. Now, we will take a short break before beginning with the keynote sessions for today.
I request all the deans and directors to join us for a group photo at the reception with the guests. Thank you.
चेयर का कहाँ रखा है? चेयर कहाँ रखा है? चेयर नीचे लाना है? क्यों? चेयर को क्या करेंगे? ये यहाँ से ले लेना।
रोड के पास करते हैं हाँ लाके रखो सेकंड होता है नहीं इधर लाके रख दिया है आपने आपने रखी हुई है अंदर ये किसने रखा उसको चलाना क्या कर रहे हो
टेप
हो गया काम हो गया
हेलो
पक्का मैं बाहर देख हाँ नहीं रहने दो मैं जाऊँ बाहर देख के आऊँ पक्का मैं बाहर देख के आऊँ सब कुछ हाँ
तो बोला कि तेरे लैपटॉप से निकाल के इस लैपटॉप में डाल, बट वो है कि लाइट्स ऑफ करनी पड़ेगी ना।
लाइट्स ऑफ हो जाएंगी जब स्टार्ट होगा।
कहाँ है मनीष भैया? कहाँ है मनीष भैया? बोलो शर्मा भैया कहाँ है?
कौन सा भी
सुन के लाइट
Frank has joined.
Oh,
That Zoom link is there.
प्लस ही ज्वाइन
Zoom link, sir. Nothing is there. Only VIP.
I think they should be there. If there is a request,
participants 2 only ना participants
this has to come there.
yeah, so that simply you just need to remove and put
Remove it. Keep it there.
read it through okay and so panel discussion 1
अच्छा इधर से उनका वॉइस आएगा ना?
इनको लंच के बाद
याद रखो
Ready करके रखो.
गिर गया okay guys 30 minutes
11:30 कहाँ पहुँच गया? 11 to 11:30. 4 हो गए ना?
11 to 1 के बीच में 4 होगा ना?
बुला लेंगे सर अभी।
But the thing is कि probably इसको
रेडी है सब रेडी
student
इसको अंतिम करो
laptop का charger to let it go in this back out of this Shiva under
ये लाइट ऑफ करनी पड़ेगी
सर वो आधा वो जो लगा है वो बीच में आ जाएगा पोस्टर नहीं बड़ी सी स्टैंड थोड़ा सा
Share the
ना नहीं वो टाइम तक
उसको pin करना.
ना बहुत हैवी भी है और वो लाइट आएगा भी ना देता है वैसा रहता है उन्होंने जैसे तक कर रखा है बहुत ज्यादा होता है अब इसमें उसके दिखता
Hello, good morning, Frank. Can you hear me, sir? Mic किधर लगा है इसमें?
You should be actually able to hear me. And you should be able to see me.
Hello, good morning, Dr. Frank. Can you hear me, sir?
Yes, I can hear you. Can you hear me?
Yes, thank you. Thank you.
Very good.
We are about to begin, sir. There's a short delay of 5 minutes, sir.
Okay.
We are waiting for the guests. They are all here. Inaugural session is completed, sir, and they're just about to join, sir.
Okay, so what do you mean, 5 minutes?
Yes, sir. 5 minutes maximum, sir. I
Okay.
will be there only, sir, with you.
No problem. Will you run the presentation from there, or do I have to sort of share it
You
somehow?
can present, sir. You can present, sir, with this sharing of the screen.
Okay, I have to see share screen. Okay, I get it. And Okay. So you see my presentation? Yeah, looks like it. Just to let you know, the room is on mute at your end. So if you tell me I should start, I won't hear you unless you go on mute. You're on mute.
Hello, Frank.
Hi, Zoe. How are you?
I can't see you. Where are you?
Huh?
There.
I'm there. Hi.
Sorry, my voice is bad. I got a sore throat.
What did you do with your voice?
Yeah, I got a sore throat.
Too much talking. Too
Yeah,
much talking.
Yes, sir.
Yes.
What about TV? TV connecting there?
Yes, sir. They're connecting, sir. It is for them too.
Okay, okay. The TV are connected. Huh?
Yes, sir.
Physical mode
Yes,
session, you can start that.
Sir, hello. Dr. Frank?
Yes.
We can begin, sir.
We can begin. Okay, cool.
1 minute, sir. Just a minute, sir. We're beginning. That is what I meant. Sorry. Please.
Yeah.
Yes, begin.
We welcome you all back to start with the first keynote session of our conference. Today, we are honored to have Dr. Frank Hasselbach, Senior Vice President and Head of Propulsion Engineering at Airbus Commercial Aircraft, overseeing the integration of all propulsive and non-propulsive power plants, including APUs, pylons, and nacelles. He leads the design, development, certification, and airworthiness management of propulsion systems while shaping Airbus's propulsion strategy in collaboration with global partners. As a highly accomplished leader with extensive experience in aero engine design, Dr. Frank has worked across Europe, Asia, and America. Before joining Airbus, he has served as Chief Engineer of Large Engines at Rolls-Royce. He is a fellow of the Royal Aeronautical Society, a visiting professor at the University of Oxford, holding a doctorate in mechanical engineering. Now, we request Dr. Frank Hasselberg to deliver the keynote lecture on propulsion towards sustainable aviation.
Hey, good morning, everybody. I still think about it's just about morning in Bhopal, I assume, or before lunch, and I'm the last thing before you and lunch, or Kishore is coming after me. I don't know. So I'm very very pleased to talk to you today, and I'm awfully sorry that I can't be with you, but there were certain things I needed to do in Toulouse today this week. So there was no chance I'm coming to India, and also I'm going next week to America. So in that respect, it was just travel-wise impossible. Otherwise, I would have been loved to come to Bhopal. So I hope you can see the presentation well, and I will now try to get through this from here. If the technique doesn't work, well, I'm sure somebody in Bhopal will help me. Good. So first of all, I'm really glad to be here. What I want to do with you, and I can see Kishore in the audience there. Kishore, hello. Long time no see. It's nice to actually at least have a visual of you. What I want to take you through is a bit of a journey of what Airbus and what the industry does to actually manage the formidable growth we have in the last 20 years, and what we're going to see in the next 20 years. And of course, we have an accountability and a responsibility to make sure that this growth is sustainable as a business and for the planet. And the first picture I choose here is, I think, a bit the topic of today. So the picture is done by one of the Apollo astronauts, Apollo 8 astronaut, in the winter of 1968. It's the first selfie of the world, with 3 people not in it because they were sitting in a small capsule circumnavigating the moon. But the rest of us, and some of us have been there, I was actually a baby, but I was there, we're on this planet, on that spaceship. And that spaceship at that time had about 3.5 billion people. Today, that spaceship has 8 billion people. And in 20 years, 30 years from now, it might be 10 billion people. And these people use energy. These people actually want to go from A to B. They transport stuff. They want to have housing. They want to have warm or cold housing. So they want to have a good life. And that good life currently uses to 90% fossil energy. And if we keep on doing this, we won't have a good life in 100 years' time. And that's why the word sustainable is in this presentation. Okay, so let's go through a bit where we are. If we look at the current landscape of aviation, you can definitely identify it's a force for good, and it's a big business. These are 2019 numbers, which are quite actual because we had COVID in between, and we're sort of back to these numbers. We have 4.5 billion passengers in the world. It might be 8 billion in about 5-6 years from now. We have about 50,000 routes served in the world. The cabin occupancy is actually better today than it was in 2019. So we're beyond 82.5. We're closer to 85 and 90% sort of usage of the cabin. And we have about 4,000 airports around the world which are serving this network. By the way, it's about 25,000 large commercial aircraft sort of doing this. Half of them are from that little upstart in the northwest of America, and the other half is from us at Airbus. Okay, so if we go on and actually look at this a bit more and dive into it, what does Airbus do? Airbus is, of course, currently, since a few years, the leader in sort of global aviation. It's a company which had in 23 65 billion euros revenue. The 24 numbers I can't reveal, of course we know them, but we will have a quiet period and we have our results on the 20th of February. The order book is a bit bigger than 554 billion these days, so it's 8,600 aircraft and a lot of helicopters and defense systems. And we have about 150,000 employees. This is a European project. This company is about 55 years old. So it's young by aviation standards, but it is, of course, now the leading company in this industry. And we're proud to lead, and we actually take the responsibility and the accountability to lead. If you look at commercial aircraft, it's about, by people, about 2/3 of the company, by revenue, more 75%. And the order book grown from the 8,598 aircraft in 23 to more 8,700 to 800 aircraft now. So we're fundamentally sort of keep on sort of booking orders more than we can deliver, which means our order book is still growing, which of course can't go on forever, because otherwise people will one day wait 20 years for the aircraft. That doesn't work. So we have to grow, and we are industrially very, very focused on growing our output up to about 1,000 aircraft a year. We're currently at 766, to give you an idea. On the helicopter side, a wide range of helicopters, from small commute helicopters to large transport and combat helicopters. It's about 22,000 employees, smaller business, 77 billion euros turnover, and the order book is much smaller, but each of these helicopters is also a multi-million euro unit, as you might imagine. And of course, we have defense and space, where we have about 35,000 employees, slightly bigger revenue than in helicopters, but a bigger order book. Here, the focus is on satellites, on air power, so transport, military transport aircraft and combat aircraft, as well as cyber security and cyber warfare. So let's talk a bit about safety in aviation. So, as I said, about 12,500 Airbus aircraft are flying as we speak. They all do about 4 to 5 flights a day. And of course, it's a bit more than 25,000 engines in service as of today, because some of these aircraft have 4 engines. It's in fact, as we are half of the industry, roughly 2.5 billion passengers are transported in Airbus aircraft in a year. And all our aircraft have fly-by-wire, which means they're the 4th generation of civil transport. That generation 4 has an unprecedented level of safety. It's about 1 accident in 25 million flights. Of course, we continue to improve this as an industry. So this is nothing where we compete with Boeing or Embraer or anybody else. This is where we work together. If we find something which is of interest for the others, we will tell them, and we expect them to do the same. Okay? As you can see, the older generation aircraft, so the ones which are more produced in the 1960s and 70s, were discontinued in 2010. They had a good safety record, but of course they were still an order of magnitude higher than where we are today with the 4th generation aircraft. I'm not sure you can see my mouse, but I'm pointing to the lowest line on this graph. If we go on, what are we doing today? So last year, just a day before Farnborough Air Show in summer, we managed to get the type certificate for the latest edition of the Airbus family, which is the A321 XLR. So it's an A321 Neo XLR. This version here is with CFM engines, so the LEAP-1A. It has actually a 30% fuel burn reduction over and above the normal single-aisle long-range aircraft you would have in that market, like Boeing 757 or 767. It is a superb sort of fuel performance machine, and it has a range of 4,700 nautical miles. That means it can do city pairs, which no other single aisle can do by a country mile. So there is nothing which comes even close to it. The only one is its own little brother, the 321 LR, which is just doing something like 4,000 nautical miles. So for airlines, it actually allows a low-risk opener of a route. And it also actually, for some smaller airlines, it allows to grow into the intercontinental market. So you can easily do routes across the Atlantic or all across Asia with this machine. The first ones were delivered to Iberia and Aer Lingus, are in service and doing well, and we're expecting to certify the second engine on this aircraft in the next couple of weeks. So that's the Pratt & Whitney GTF. Let's look at Airbus in India. Airbus has quite a history in India, and it is quite a future in India for Airbus as well. We have about 3,500 employees. The majority of them sits in Bengaluru, in the sort of south of you, and we effectively sort of procure roughly €1 billion sort of euros of goods every year from India. We are generating about 15,000 jobs across the supply chain in India, and of course we have, thankfully, very, very powerful and great Indian customers. Two of them are actually shown here, so Indigo and Air India, and recently met Kemper Wilson from Air India, and fundamentally you can see the trust they have in us and the trust we have in them will be a good foundation for the future. We also have a lot of other sort of links to India. So we have the military transport aircraft C295, where the Indian Air Force ordered 56, and 40 of these units will be locally produced in India. We have the first helicopter FAL in the private sector, partnering with the Tata Group, and we have about 800 firm orders from these two big companies in India, Air India and Indigo. And of course, that means we like India. We're very interested in India, and Kishore knows, and Suresh as well. I'm every year in India at least 2 or 3 times, and I'm really interested in learning different places and so on. And you can, as a testify, I'm also doing my holiday in India in about 2 weeks with my family. So I will be touring your country. So I'm looking forward to that. Let's go on. What do we do in Airbus propulsion engineering? It might be interesting to understand what does an airframer do, having in mind we're not doing the engines. There's a lot to do, and I'll give you an idea. The team doing this in Airbus, so my organization is about 1,500 engineers. So a lot of engineers not to do engines, which means we have about 900 internally, and we have about 600 externally to Airbus who works this, and we're working on the in-service support of all the aircraft. And in the beginning of the sort of development, we're talking about the overall engine specification and integration. We do the pylon design and build here in Toulouse. We certify all the integrated product and subsequent modifications of any engine and propulsion system of an aircraft. So we are the certification team. We have to validate and verify throughout the life cycle all the modifications and stuff which happens to these aircraft. We, of course, and I personally drive a lot with the big engine companies, i.e. General Electric, Safran, or the combination of the two, CFM, as well as Pratt & Whitney and Rolls-Royce, their research and technology. So we're looking at what they're doing and why they're doing what they're doing. They tell them what they should be doing, and we're effectively influencing their technology strategy as well. Of course, we assess the engine performance. We're trying to optimize it in the aircraft. You wouldn't believe how much loss you can generate by wrongly integrating an engine or by having the thrust vector pointing slightly in the wrong direction. Of course, we have to manage the integrated engine control, and our computers need to speak to the computers of the engine well, and we have to have absolute control of the engine. We are modeling the acoustics of the whole aircraft, not just the propulsion system. So that's a decision Airbus took to make sure that, so external and internal noise in the aircraft comes from one source. And as propulsion is one of the biggest sources for noise, we decided to actually have it combined in the propulsion engineering team. We do the overall nacelle integration. The nacelle is effectively the cowling around the engine, which has certain functionalities like guiding the flow into the engine and around the engine, making sure that you can do thrust reverse, and managing noise and fire management. In case you have a fire, you have to do ability to extinguish it, and then all of that happens in the nacelle and the pylon. And then, of course, the integration of the aircraft and the engine subsystems. So that's what we do. And we do this on the flying fleet to 50% and for the future to 50%. And I'll come to that now. So if we look at what we expect from partners, we want a reliable partnership. So our partners are the engine companies and the nacelle companies. We want competitive, reliable products. We want cutting edge, proven technologies. We want to have integration capability and systems engineering at the highest possible level. And to be fair, we're getting these from these companies. They are doing the most complex products on this planet. We effectively want world-class servicing network and capabilities. We, of course, need solid industrialization base and supply chain. And we need the ability, i.e. the financial and the resource ability to contribute to complex, multi-year, multi-decade programs and endeavors at a global scale. And of course, in other words, the engine shall weigh nothing, cost nothing, use no fuel, have infinite life, and clean the air as it flies along. Of course, that's a bit of a joke, but it gives you an idea. We are the customer, and we really need the best they can give, but we also value the capability these companies have to a large extent. And maybe at this point in time, I'll say a word about longevity. Aviation is a wonderful business. It's a very, very unique business. As I said earlier, we have 4.5 billion customers, passenger. They are served by roughly 100 airlines, which getting their planes from 2 companies. So we have 100, 4.5 billion, a unique business. And then you have 4 engine manufacturers, 10 to 15 major system suppliers, 200 sort of subsystem and sub-tier suppliers, and maybe thousands of part suppliers. So it's an interesting business of huge sort of supply chain with one bottleneck in the middle, which is Airbus and Boeing. And there's a bit of Embraer and a bit of Comac, so let's be fair. But those are the ones who are dominating it. So have in mind, and then we're doing products which last lifetimes. Our products last the lifetime. So we are effectively, when we're working here today, I have people working on the A310. I have people working on the A340, on the A330. A330 is still in production since 30 years. And it will be in production for another 10, 20 years. So we have, if you go into the industry worldwide, you can see there are airframes which maybe actually are in operation for more than 70, 80 years and get re-engined multiple times. So we are an industry where the products are small, sort of small in size in terms of we don't have many different products, but the products last generations. So let's go on. Those are our partners. Honeywell for and Pratt for the APUs, Safran, Collins for the nacelle, and then of course all the major engine companies, GE, Pratt, Rolls-Royce, and the combination of them underneath IAE, CFM, or Engine Alliance as our sort of engine suppliers. This is how we do this. You can see for the wide body we are mainly single source now, so it's effectively all Rolls-Royce. On the 220, we're single source with Pratt & Whitney, and on the major product, the A320, which is it's now at a serial number of 12,500 to give you an idea. It's half LEAP, so CFM and Pratt & Whitney. If we sit back and now talk a bit about sustainability, I'll try to speed up a bit. I think it's worthwhile to look at aviation overall. There are actually 4 revolutions in aviation. The burst, powered and controlled flight. You might not know that, but by nationality, I'm German. Also, I lived a long time, about 20 years in the United Kingdom. And of course, as a German, I would say there was Otto Lilienthal with a glider 10 years before that. But he didn't have an engine and he didn't control his flight with control surfaces. This is the merit of the brothers Wright. And that is, of course, 122 years ago on the east coast of North America. That was the first revolution. The second revolution was then, to be fair, a German-British one, invention of the jet engine. That allowed higher speeds and higher altitudes because they actually could work in rarefied gas, so in high altitude. And then it had less drag and it allowed bigger speeds, especially also because it's a reaction engine and not a propeller engine. Then we had safety as a means of civil mass transportation. That came into the 60s and 70s. This is where the wide bodies were formed. By the way, Airbus can claim doing the first wide body as a twin, which was the A300B. This is effectively the first, that is about 53 years ago, first Airbus aircraft flying in Toulouse. But it also was the age where, because the aircraft got bigger, the engines got better, the engines got more reliable. Effectively, it started where people were flying on holiday. So that was definitely a revolution. That was the explosion of aviation as we know it today. And then, of course, now we have the accountability, the responsibility, and the privilege to work on making this business sustainable for the business and for the planet, and thereby for mankind. If we look at this, sustainable growth is there. We have reduced CO2, so fuel reduction by about 80%. So compared to the 1960s, 1950s, aircraft today per seat use 80% less fuel and consequently do 80% less CO2. We have a significant reduction in NOx, so nitrogen oxide, by about 90%. Huge noise reductions by 3/4, 75%. And of course, we had targets for 2020, which we almost met everywhere. And then we had targets for 2050, and that's what we're talking about now. And that target is now net zero. 10 years ago, if I would have given that presentation, the target would have been halving 2050's carbon predictions. I think the industry itself got more ambitious, and it realized, looking at the global warming index of 1.5 degree, which we are now above the pre-industrial age, it means we have to do more. So we're targeting net zero by 2050. How do we do that? Well, there's a plan. That plan is best expressed in terms of emissions. What you see on this chart is CO2 emissions by millions of tons. So 1,000 clearly means a billion tons. And we are roughly here. So we are roughly at a billion ton of CO2 emissions, which means if you divide it by 3, roughly the amount of fuel we use, and that's correct, because in the year we currently, these 25,000 aircraft use about 340 million tons of Jet A1. So that generates a billion tons of CO2. That's just a simple chemistry. And if we wouldn't do anything on the fleet efficiency and simply grow aviation up to something like 40,000 aircraft or 50,000 aircraft in 2050, we would end up with about double that number, 2 billion, more than 2 billion, 2.5 billion tons of CO2. If we deliver to our promises and to our customers the more fuel efficient aircraft I was talking about earlier, because all the aircraft today which we are selling are about 20 to 30% more fuel efficient than the generation before, we actually are about 10-15% better. If we keep on working on the technology for the next generation of aircraft to come, which we will put into the market next decade, then we get this dark blue wedge underneath. So we will effectively get something like another sort of 20% reduction of CO2 emissions in the year 2050. Then we have operational measures which we can use to drive a further reduction, for instance, flying in pairs, in flocks like geese. We actually did a test, you wouldn't believe it, with 2 A350 flying over the Atlantic Ocean in a formation like geese, like wild geese traveling across the country. That formation, they were about 1 kilometer apart. So where the second aircraft uses the wake vortices of the first aircraft to reduce its fuel consumption, that fuel consumption was reduced by more than 5%, in some areas up to 10%. So there is some logic in operational measures, and of course you can optimize routes and other things. And then the biggest part is this green part here in this chart, and that biggest part is the use of different fuels. Not using fossil fuels, i.e. don't use oil and gas coming out of the ground, where the solar energy of the past 250 million years ago had been stored over many thousands of years, and we are effectively just using it in a few years. And go and say, oh, I'm doing feedstock, biofeedstock, synthetic fuel, or power to liquid synthetic fuel from solar energy and wind power, so renewable energy sources, and thereby generate an ability to actually not have fossil fuel. And I'm not adding to the carbon budget of the world. However, I'm still emitting CO2, but I'm also capturing it at the same time. So it's a closed cycle. It's about an 80% reduction in CO2 against fossil. And then, of course, the last thing is I can capture some of the carbon and put it into the ground or put it into fuel production and thereby also do something. And that's the way we will achieve net zero by 2050, or will become very, very close to it. What can we do? So let's talk about that dark blue triangle in this chart. So the second from the top, the new technology. What can we do on aircraft? Disruptive technology means lighter weight materials and an element of hybridization, i.e. using electrification more in the aircraft. But those are nice things, but they're not the main things. The two main things who actually make an aircraft better is the wing, in terms of its span and its L over D, so its lift over drag, and the engine. Those are the two things which make aircraft better. And that's effectively over the last 60 years, the way aircraft got better. And it will be like this for the next 50 years. Let's look at this a bit. If I take the baseline, that's now percentage of SFC and fuel burn against the Comet aircraft in the 1960s. The engine fuel consumption roughly halved since the 1960s, with the aircraft fuel consumption went about the so-called 80%. So why is this? So the interesting bit is in the 60s, 70s, 80s, the aircraft got bigger and bigger and bigger. This is a number per seat. So it clearly shows you the aircraft got aerodynamically better, but they also went bigger, and that drove massively the reduction. In the last 30 years, you can see a majority of the reduction actually comes from the engines, because these two lines are parallel from 1992 to now. Why are engines getting better? Well, engines getting better in two ways. And this is a very simplistic view of that. You can see the engine-specific fuel consumption here on the y-axis, which means fundamentally pound of fuel per pound of thrust an hour. And a good number to have in mind is about 0.5. So that's where engines today are roughly. You know, small engines are big higher, large engines are about there. The engines of the last generation were more at 0.6, and the theoretical limit is closer to 0.4, 0.35. And what I've plotted here as a function of a parameter is the propulsive efficiency on the sort of, let's say, lines, where the lines of constant propulsive efficiency are the ones which go from the lower left to the upper right. And the other carpet lines are the lines of constant thermal efficiency plus the transfer efficiency, i.e. the LP turbine and the fan efficiency. That is what you have for, these are the lines going curved from the lower right to the upper left. So today we are roughly at propulsive efficiencies of 80%, and we are at thermal efficiencies around about 47%. We can actually improve this by increasing the overall pressure ratio and the turbine entry temperature, reducing the cooling in the engines, and increasing the fan size at a constant thrust. That means reducing the specific thrust of the engine, i.e. making a smaller pressurization. Of course, that means the engines are getting bigger and bigger and bigger, and you can notice that in the aircraft of today, and in the future there will be even more. And we even have a debate of whether we could actually make very big engines which don't have a casing anymore. And that is exactly the question of today. And one of my key jobs, after having spent a career in engine making in Airbus, is to help Airbus to understand what is the architecture of the future. And that's what I'm doing. So I didn't speak much about me, but you heard it in the introduction. But fundamentally, I spent 30 years in doing engines, 25 of those for Rolls-Royce in the United Kingdom. And now I'm effectively sitting in Airbus since 3.5 years. And my main job, besides keeping the fleet safe, is to make sure that for the next generation of aircraft, we get the best possible propulsion system and integrate it in the best possible way. And we have two options. We can actually go and do more of the same, i.e. have some geared turbofan architecture with a bypass ratio of 14, 15 or so, and sort of do what we always done, and that will be a few percent better than the before. Maybe 5 to 10, I don't know, in that territory. Or we go down the route of saying, well, we do a real paradigm shift. We do an architectural bold move and go to an open fan, which has a much more potential of actually improving the fuel efficiency. However, it has integration challenges like, oh, there's no casing anymore. I have to shield the fuselage against fan blades or parts of fan blades in a certain area. I have to manage external noise and internal noise. I have to think about how the wakes interact with the wing, because some of them will go over the suction surface of the wing. And I have to sort of worry a bit about maintenance cost. And maybe I have longer debates with the regulators about the certification of this motor. But that's exactly what we're doing today. All of this we're investigating. We have decided to do a flight test demonstrator of that engine on a test aircraft. It's nothing to do with a potential solution. It's just bringing this engine closer to a wing and understanding the integration of it and understanding how it actually operates in flight. So that flight test demo will be in about 2 to 3 years from now. We're in the middle of working this. We're working this together with CFM, and we're working it since 2.5 years. So more or less, when I came, I looked at it and said, okay, let's start that. That looks interesting. The other thing we're doing, we're looking at hybridization of propulsion systems. It's a bit like in cars. So, you know, in cars, there was, first of all, simple thermal engines. Then these thermal engines with Toyota effectively got the first help of having an electric motor and generator, which was sort of linked in order to optimize the off-design behavior of the engine, the fuel efficiency. Then that came to plug-in hybrids, where people had sort of energy storage other than fuel on board with batteries. And then eventually got to electric cars. Well, cars are different than planes. Cars spend 90% of their time sitting somewhere on a drive, whilst planes have 90% of their time in the air. So just charging batteries isn't that easy. And also the batteries are not power dense enough to do anything meaningful. So you wouldn't be able to fly a large aircraft over the Atlantic on the basis of electric stored energy in a battery, because the battery would be about 20 times heavier than the plane itself. However, what you can do is you can say, well, I can optimize the off design, so effectively sort of takeoff, landing, idling, and so on. So all these things which are taxi out, taxi in, takeoff, climb, and descent, where I actually have smaller issues with the turbo machinery, operability challenges, stuff which demands that I have some margins in the design, which I could take out if I have some electrical power of maybe a few percent of the total power of the engine, just helping on these edges. And that's what we're looking at. That might be a few percent fuel efficient overall, having in mind that I have more weight and complexity because of this. But it's worthwhile. It's worthwhile for short haul and medium haul aircraft. It's not worthwhile for long range aircraft, which actually spend most of their time in the design point in cruise. So that's what we're looking at. It's quite exciting. So a lot of the team is involved in this. And of course, we're working with system suppliers, partners, and engine companies to do that. Which brings me to the last slide and the end of this presentation. And then I'm happy to have a couple of questions if there are any, and we have time. So the key message is Airbus is really committed to the decarbonization journey. We are currently working on our current portfolio, which is 50% SAF compatible now, and we're doing incremental developments of our current portfolio. We're investing about 2 billion euros into this alone every year. And then another 1 billion euros goes into the preparation of the new short and medium range aircraft and the potential regional hydrogen aircrafts of the future. That's where we're spending the other money. So you can see we have quite a committed portfolio. So in total, about fairly constant over the last 5 years, 3 billion euros per year going into that type of work. And in order to sort of more or less pioneer the lower emission or the zero-emission aircraft of the future. And of course, in the long run, in the second half of this decade, this will go to the short-range and long-haul market in some form. So it's a staged approach. We're in stage one in the lower quarter to the left. The next 10, 15 years we will spend in the middle of this chart. And then, of course, we are in the second half of the century. And I will be really excited. Unfortunately, I will personally most likely let's see it, what the teams do then. And as I said, aviation is a generation-spanning undertaking. I know the products I'm working on today, the products the team is inventing for the next 5 to 10 years will be products which will still people working on at the end of this century. So with this, I thank you, and I'm happy to take some questions. I can't hear the room. Just yeah, I can read it. Good, thank you.
Full screen video. Full screen. Do that.
In case somebody's speaking, I can't hear anything, but I know I hear a bit of noise from the room, but don't know whether there are any questions. Doesn't seem to be the case. Very good. There's one.
Mic is provided.
Mic, go to mic. Mic. Camera. Camera.
I see somebody in the front waving his arm. So easy.
Am I audible? Am I audible?
Yes, yes, yes.
Hi. Okay. Actually, you talked about long range and short range, right? You talked about long range aircraft and short range aircraft, and told that for long range the sweet point is applicable. So for the short ranges, different approaches needed. So what percent of market actually depends on the short range and what percent for the long range aircraft? Any idea on that?
Sorry, I didn't catch the question. Can somebody closer to the mic? So you had a question. I understood long range and short range, but I didn't really. So
Okay.
what's your question?
Actually, there is a market for the short range and market for the long range. Correct?
Yes.
So what is the percentage of market for short range and long range? How is it divided? 50-50 or 40-60?
Okay. So it's an interesting question. So you have to be careful. By numbers, of course, 75 to 80% of the market is the small medium range. So the A320 class. That's about 75 to 80% of the market by number. By revenue, it's slightly different. By profit, it's again different. By profit, I won't talk about, but fundamentally by revenue, it's much more that you're actually making. You have a bigger business in the long range, so it's about 40% in terms of revenue because these aircraft are more expensive, and they're considerably more expensive than a narrow body. That's number one. And of course, also the utilization of these aircraft is higher. If you look at the long-range aircraft, the utilization number will be 5,000-6,000 hours in the year. On a shorter medium-range aircraft, it's about 3,500 to 4,000 hours in the year, which means that the engine companies make a bigger revenue on the wide bodies than on the short range, because fundamentally they have, of course, in most of the cars, time and material or power by the hour agreements. So if you look at the total revenue in aviation, I think it's half-half. Small medium range is half, and wide body long range is the other half. Also, the numbers of wide body aircraft are much lower than the numbers of small medium range.
Yeah, so sustainability wise, where should we focus? Whether it's more, right? Whether it's short range.
We need both. There's no focus. We need both. There's no debate, and we're doing this. Clearly, we're having lots of improvements on our wide body range. So A350, A330neo. and lots of focus. There are continuous engine packages to improving the product. There are continuous sort of aircraft optimizations, new functions in the aircraft, because this is quite important to make money in both places. So we're not really preferring the one over the other. We're focused on both. But it's normal for an aircraft manufacturer who starts with smaller aircraft and slowly grow, and you will see that with some of our competition, and it will take decades to get there.
Excellent. Thank you. Thank you very much for your answer.
Please. Wait. Sir.
You mentioned about the aeroacoustics studies that is done for the aircraft. I would like to know how much of this is experimental and how much of it is numerical simulation. Like, are you doing largely simulations for the aircraft to get the acoustics, or it is mostly experimental?
Okay, it's good question. Thank you very much. It's actually both. So we have various, of course, wind tunnels in Europe and America, which we use for sort of acoustics. We have a large one in the Netherlands, the Dutch Netherlands low-speed wind tunnel, which has very, very good capability for noise measurements. And we do noise measurements mainly for source definition. We have smaller noise measurements for all the systems in the aircraft, because internal noise is dominated by pumps and hydraulics and other things and so on, and vibration. So there's a lot of testing going on. On the modeling side, you said it, large eddy is in there. There are some Boltzmann methods which we're using. There's a huge undertaking in Europe to work on even more sort of lattice Boltzmann tools of the future, to actually have boundary layer methods and other sort of boundary element sources in there. We do have, of course, also a lot to work on the transfer of noise, the mechanical transfer of noise, the reflection. All of that happens in there. So we have integrated, coupled computations, all of this. So you are pretty able, or we are pretty able today, to predict noise in the cabin and the external noise. Not perfectly, and for certification we still have to do tests, of course. But for modifications, sometimes we can do this by analysis. If we show the tool is really, really helpful. And of course, in troubleshooting, because every aircraft you deliver will have a small issue somewhere, it's very helpful to have good capability to say, okay, so if it sounds like this, it must be this seal, it must be this door, it must be this rivet somewhere. So that's all there.
Thank you. Thank you very much.
Good morning, Frank. It's good to see you.
Good to see you, Suresh.
Okay. Sorry, I have a bad throat, so you might be hearing me in a different tone than what you're used to hearing. So thank you very much for the very interesting talk on the future of propulsion. My question is related to sustainability. You also mentioned about SAF and hydrogen. What do you think are the challenges that you would face as airframe manufacturers towards certification? Because that would be, towards when you talk about towards commercialization, putting into service. What kind of challenges do you foresee in certification?
Okay. So SAF, not a big one. Clearly the aircrafts today can fly with, they're all certified for 50% SAF anyway. They can be easily certified for 100% SAF. You have two different sources of SAF, or forms of SAF. You can call it drop-in. So sustainable aviation fuel, which has exactly the same specification than Jet A1. We call that drop-in because you could actually mix it with Jet A1 without generating any complexities. And that's effectively 100% for the aircraft, because you will have no detrimental impact on the aircraft, the seals, the fuel system, nor the engine. But of course, if you want to have 500 million, 600 million tons of SAF Jet A1 in 2050 by biofuels, that won't be possible. There's not enough feedstock in the world to do that. So you need synthetic fuels. Synthetic fuels won't have aromatics in this unless you artificially put them in. And then the fuel is different. It doesn't fulfill the spec A1 sort of spec anymore, and you have to recertify the aircraft and the engines for it. But that, with modern engines and aircraft, is also not a problem. So I suspect the industry will go from drop-in fuel to sort of non-drop-in synthetic fuel over time. On hydrogen, it's a different story because you fundamentally have to work on completely different fuel systems, storage systems in the aircraft. It's stored cryogenically, liquid, and that's a much bigger feast, and we have to go carefully from technology demonstration to subsystem demonstration to aircraft demonstration and then to certification. But it's a long technology journey on hydrogen. Okay?
Thank you very much, Frank.
Good. I think maybe one more question, but I'm afraid because we are later than we originally thought, I have to change place here in Toulouse to go to a different session. So off you go.
Yeah, good morning, Frank. It's Dr. Uniappan. Related to that, right, long range and short range flight totally. In coming to the sustainability point of view, right? If you take a long range flight, if you take a A350 or A380, it is going to burn, 6 to 8 tons of fuel per hour, right? It's like a drag mass. If you wanted to fly for say 8 hours continuously, you have to carry 60 to 50 tons of extra drag mass fuel in the aircraft. You agree with me, right? So, in the sustainability point of view, in order to reduce the carbon footprint, is it a good idea to have, right, the medium range flight, land and then take off? That is the more efficient.
Yeah. Good question. I think that's perfectly correct. If you would actually fly only 4,000 nautical miles rather than 8,000 nautical miles, you would burn less fuel because you're lighter in average throughout the flight. There are some downsides. You actually use more of the airport. You have takeoff landing. You eat more of the life of the engine. There are these things in there. So we have to be careful of that. If you would have that in mind and design the aircraft for it, would be even better. But then, of course, it's down to how do you grow the overall aviation sort of stuff. The other element you could do is you fly slower. It's a bit like if you drive your car 150 miles an hour over the motorway or 100 miles an hour, it's a fuel consumption difference. And that's the same for planes. So you could fly instead of Mach 0.85, you could fly Mach 0.8. And you would save fuel about 20%. However, you would actually need more aircraft. So I think we like that. We would be big fans of it. People fly slower, just buy more aircraft. Great business. So there's a dynamic in all of this. There's also a commercial element you have to have in mind. There's the pure mass and physics, and then there's the pure mass and physics of the financial market. All of these companies have to deliver, and you will want to pay a certain price. So if you think this to the end, flying shorter, flying slower means airlines have to buy more aircraft. They spend more money. They will recoup it from you. So you would get for flying shorter and flying slower more money. You have to pay more money for your ticket. It's a big system.
Yeah, understood. Yeah, you have to do data analysis, right? For example, which one is the more efficient, right? We have to use data science to gather this, right, and then do the optimum fuel used for the flying hours.
With existing aircraft, it's always a bit of a suboptimum because they were designed for something else. But nonetheless, it's a fair comment. Physics don't lie, but there are also market physics. Okay.
Thanks.
So thank you all. I hope you have a good rest of the conference, and thanks for making possible that I actually could do my talk a bit earlier because of the meeting I have now to go to. I don't know whether I sort of took your spot, Kishore, because of that, and you are now. Then thanks for making space. Okay, guys, have a wonderful rest of the meeting. Cheers. Bye.
We thank Dr. Frank for such a knowledgeable insight on aviation.
Dr. Kishore Jayaraman, Chairman UKIBC, United Kingdom India Business Council, and Strategic Advisor, former President, Rolls-Royce India in South Asia. He has played a pivotal role in shaping the strategic direction and expansion of Rolls-Royce civil aerospace, defense, and power system businesses over the past 10 years. A strong advocate for technical innovation, he has spreaded the development of Rolls-Royce digital and engineering capability in India, contributing significantly to global projects. He also led the expansion of companies' manufacturing and sourcing presence in India throughout the joint ventures and key partnerships. Before joining Rolls-Royce, Dr. Kishore held various leadership positions at GE for 23 years, including President and CEO of GE Energy South Asia. Based in New Delhi, he is actively involved in multiple boards and industry committees, promoting sustainability and ecosystem development. In recognition of his contribution to international trade, Dr. Kishore was awarded an honorary officer of the Order of British Empire (OBE) by Her Majesty the Queen. Now we request Dr. Kishore Jayaraman on the stage for delivering the keynote lecture on Future of Sustainable Aviation.
Okay, there I figured out the button to turn on the mic. Good morning again, everybody. Good to see you all here. Great to be here at the VIT campus in Bhopal. I wish to thank all of you, including the Vice President of VIT, Professor Suresh Sampath, and the rest of the faculty here who have made it possible for me to come here and share some thoughts with you. So look, when I was thinking about what is the future of sustainable aviation and said, do I want to really go through about 5 or 6 slides here and talk about it? I figured it's best to just keep it simple and try to figure out what's been going on, why this is going on, and then say what's happening today and what's going to happen into the future and why it's going to happen the way it's going to happen. So if I simply segregate it into these 3 different pieces, what is happening is climate change has been a conversation topic, and it has been going on for quite some time now. I would say easily 20 years. But then it took the front stage when global warming was obvious, people could see it, and more and more focus came in. There was a tipping point where climate change became a serious issue for humanity. And at that point in time, people started saying sustainability has to be part of the corporate initiatives. And then as part of that, when you look down into aviation, and they started looking at what are the biggest pollutants, of course, fossil fuel plants, and of course, that's the energy sector, but then it's the propulsion. It is, and then when you look at propulsion, transport, automatically you come down to saying, where does aerospace stand in this? 2 to 3% of all the carbon emissions come from the aviation sector, right? And the aviation sector contributes almost, I would say, 1 billion metrics of emissions. And if you put this in perspective and you say, if you put the world 192 plus countries, aviation alone would be the top 10 emitters if aviation was a country. That's how important it is to understand why the aerospace sector is extremely important for sustainability. And now that it was very clear that this is essential for the aerospace sector to be, put the most focus in order to do this. So we started looking at it, the propulsion systems guys, engine developers, Rolls-Royce, GE, everybody jumped in, and there were viewpoints as to how to make it better. Everybody looks at efficiency, but that's a commercial decision. Rolls-Royce alone has improved the efficiency by 15%. GE has improved their efficiency by similar amounts, if not more or less. And at the end of the day, the efficiency gives you better burn, which means lesser emissions because you're using less fuel. But that's not enough. Then they said sustainable alternate fuels, SAFs, as you must have heard. Then SAF testing went on, And everybody said, I got to do SAF testing now, and they all did it. So today, if you look at Rolls-Royce or GE, their engines will be 100% compatible. But only 50% by regulation is still allowed. But an even bigger problem is the fuel itself. The availability of the fuel does not lend itself so easily to it. And so what has happened is that you start looking at it and saying, now we've got to build a whole ecosystem to it. I got to have fuel. I got to have the propulsion systems that will absorb the fuel. And I got to figure out how to monitor this whole thing and manage the whole thing. But that's not just it. It's got to be more. And so what is more? You look at the aircraft designs. You look at alternate fuels. Look, hydrogen as a fuel cells coming into aircraft. EasyJet and Rolls-Royce tested one. So they took one engine and put it as hydrogen-propelled fuel cells. It worked. But will it be commercially viable? Will it be commercially viable becomes the biggest question. And today, even with SAF, it's still not totally commercially viable. But what is happening is the aircraft designs are changing. Did you see the picture when Frank was showing it, where the aircraft wings have become thinner? And I think it's like the long wings with a different aerodynamic design is being all brought into the fore. And why is that coming about? Because they got to think out of the box. No longer are we going to have a plane that has this and this and this. Can be changed. And that's what people are looking at. The same thing with engines. Can we use different materials? And by change of materials, you reduce the weight of the engine. You allow more passengers on the flights. You look at the seats configuration. You look at the body of the airplane. Everything is being changed today. And what is driving it? Sustainability. Efficiency is always the case. Reliability is a given. In the aviation sector, reliability is a must. Safety is no compromise, right? So now you look at this and you go like, what is happening? There was an idea, and the idea became, oh my God, that is the climate change and sustainability. We got to do this. What's the second step to it? Implement things. So every company today is trying to implement whatever they can to show the world that they're green. Hotels, the transport sector, shipping, logistics, infrastructure, power sector, everywhere is the same. Aviation is no different. Now, as you take this forward, what is going to happen? It is not necessary just to get some fuels that will power the aircraft. Where do these fuels come from? If you get hydrogen, where does the hydrogen come from? You got to start looking at where does the hydrogen come from? Is it green hydrogen? And so then you start looking at how do you produce green hydrogen? Same problem again, cost. So it is still where, if I look back in my GE Energy days about 20 years back, solar was not a viable thing at all. Nobody wanted solar. It was very expensive. Coal plants were the easiest to build. Gas turbines, natural gas was a little bit expensive, but very clean. Then came wind. Finally came solar, which nobody believed will ever come through, and today solar is everywhere. Similarly, in aircrafts using SAFs might be the next step. Eventually getting over to an electric aircraft will be the last step, possibly. Rolls-Royce built the first electric aircraft called the Spirit of Innovation. This aircraft did 387 miles per hour speed. The next step was to say, do we take it forward, cross the English Channel, put it across the Atlantic? They all started thinking about it, but then all the electrification slowed down. Why? Because first you need to figure out how you're going to convert from fossil fuels. You can't go from fossil fuels, it's not disruption. It is going to be incremental. And so the incremental has to go more and more and more. People have to be acceptable more and more and more. Finally, we'll get electrification. If you look at today, air taxis, if you don't believe me, just now I'm working on a project in Chennai, where they want air taxis in Chennai. Okay? And would we have ever thought about it? And these air taxis they're talking about are not just helicopters. They're talking about electrical vertical takeoff and landing systems. These are nothing but a really nice acronym for an electric helicopter, right? But if that were to come true, you eliminate so much of the crowds on the roads, which is again elimination of any kind of fossil fuel emissions on the ground. But if the aircrafts, electric aircrafts, the batteries are charged by a power solution that is not green, then the concept is lost. So where am I going with this whole thing? I'm saying all this because an idea is great, implementing is very important, but you have to constantly innovate it to take it to the end point. If you cannot bring yourself to say that I need to be 100% sustainable, and you're not able to get there, there should be a path to get there, and that's where the innovation comes into play. So I want you to remember, after I leave here, the 3 I's of sustainability. Then put in a bucket where everybody stands, every sector stands. But one thing is for certain, as you look into the future, it is 100% going to be there for. And I think the younger generation here, I may not live to see an electric aircraft flying people, but I think you will definitely be part of the technology development that will bring out an electric aircraft which will actually fly people around the world, right? But all this, the other issue is, the bottom line is businesses cannot do it if it's not commercially viable. So right now, if you try to sell some of this stuff, it's very expensive. None of us in this room wants to pay for it. So that slows down the process. But even let's assume, how do we get to that point? It's going to be the interaction of 3 key factors: the academia, the industry, and the government. And you know what's interesting is every government, every institution, and every industry in their own little countries or in their own little continents are very happy collaborating. But if sustainability is going to be there for humanity, it has to be something, a collaboration that will work across borders. So the Paris climate change was great, but if you look at it today, I think there are some countries in the world who are saying, do I really want to be all this sustainability, climate change? Do I need to think about it? And these are countries who are relevant. But that should not slow down the whole process. India has said by 2070, India will be carbon neutral. India, the globe has said by 2050, there'll be net zero. There's a UN charter to that. People have signed up to that. And India is doing so much. India's plan is to spend $100 billion on hydrogen mission, to build hydrogen. India is betting big on hydrogen, right? Will it all come to the fore? Will it all happen? Time will tell. But is there a tremendous amount of interest in there? Is there a way for all these partnerships to work? It's fantastic. But as students here, as faculty here, I think the 3 things I said, the academia, government, and industry partnerships are going to be here. It is something that we all have to be part of. And it is not going to happen by us in silos. It's going to happen by us all being together. I'm going to stop there. I don't know if there's any question and answer or anything, but I do believe in this topic. I do believe sustainability is here to stay. I do believe that we will do all the right things and technology will be at the forefront, whether it's aerospace or 10 other sectors. So I'll stop there. Thank you very much for the opportunity. Great to be here. Not sure if I'm standing here for Q&A or do you want me to?
I will ask you.
Okay.
A very good afternoon, sir. I have actually 2 points to ask you. Basically, my first is that you already mentioned something related to air taxi and you're working in Chennai. And if the news is correct, or if I have read correctly, in Bangalore airport, already plannings are going on related to air taxis.
Yeah.
And maybe by next year, early next year, they'll be launching it. China has already achieved also. If No? No.
I think the closest one is Joby Aviation trying to do it in Dubai. I think Dubai is trying to get it all done by 2025.
Okay, sure, sir. And sir, related to the electrification and EVs that you have talked about, my only concern related to EVs is about sustainability. When we say batteries and EVs and lead and lithium and all these things, so they are also going to create a lot of waste. So how EVs can actually help in sustainability?
Well, actually, I honestly believe that it's only probably 30% of the sustainability that you get with EVs. And you raised a very important point is what happens to those batteries. But as we speak here, I have read that the batteries, there are companies which are trying to figure out how to repurpose the batteries. right? And so the repurposing, if it happens, again, it's all a cost again. See, all these technologies that get developed recently, the issue is that these technologies end up costing a lot to the consumer. And that's where that is in the repurposing of the batteries. But then there are other commercial models that are available where these batteries are bought over by people who rent the batteries. And there's a lot of things. And today, the EVs that are sold in India, I'm told that you'll only have about, 4 years or 7 years in the battery life. And the question is, do you really have to buy a new battery? Or will they do something with that battery, recharge it? I don't have an answer. Maybe if anyone has, that's great. But I don't think I have an answer on that. Disposing it is a problem. The disposal of the PCBs, the disposal of the electric components of computers is a huge issue. And in India, there are mandates. I don't know how many companies actually know this, but you really cannot take your PC that your company uses and throw it out in the street. There are procedures to do it. And when you're importing, there are licenses to be obtained. It is very complicated world in terms of disposal of a lot of this stuff. And so, again, the batteries are being charged now. Do you use green power or do you use regular power? So, a lot of questions to be answered. So, I think the EV is about 30% of the journey. I think the rest 70% is yet to come. The movie is still open.
Yes, sir. Thank you so much, sir.
Yeah.
Thank you very much for a very interesting talk. And your passion for sustainability is very evident in the way you spoke. Hence, I want to ask you a very philosophical question. Given that there are lots of oil reserves, plenty of oil reserves, fossil fuel reserves, and there are countries which own them, and also given that the current political situation that the US is taking a step back on the Paris COP Accord, what is your view on future sustainability, and are we going to lose the momentum in the bargain? Where do you see this?
See, I think Malcolm Gladwell's book called The Tipping Point applies. Right. I think we are at a tipping point of where I think everybody senses, every human being today has been touched by saying that this is a very important topic. And so I don't think it'll die, but I don't think it is going to go and people setting targets of saying in the next year I'll do this or next 5 years I'll do this. Those aren't reasonable. I think there's a balance. The 2050 goal will still remain. And if you look at India, India is going tremendous into renewable energy and solar. I'm sure there'll be an outcome with hydrogen. And even if outcome is hydrogen is not there, the existing coal will be converted to natural gas. There will be a journey that will happen. The slope of acceleration of that journey is a question mark.
My only concern is that the goalposts should not be shifted.
Yeah. Well, yeah. So far, politically, I've not seen the goalpost shifted, but I don't know.
Thank you. Thank you very much.
So thanks for the wonderful presentation talk. I have a question that the previous speaker said, converting Airbus into electrification. It is almost not possible because it almost requires 20 times of the current Airbus weight. You also mentioned that you have already tested an electric aircraft. So how is it, and can you give
So look, some of them are research projects. not thinking about all these things. So I think we are getting there. It's going to be slow, but we'll get there.
Thank you, sir.
Okay, so there are no further questions. One last point from me. Rolls-Royce today is a company that's on aerospace and defense. Rolls-Royce cars are owned by BMW. And I have given the speech to you as an ex-Rolls-Royce aerospace and defense guy. So I'll leave it with that. Thank you. Have a wonderful day. Appreciate it.
Thank you, sir. I'm sure we will achieve a sustainable world one day. Now, I would like to call our conference chair, Dr. Prashant G.K., to offer a token of love and respect to Dr. Kishore Jayaraman.
Moving on to our third keynote of the day. Dr. Theophilus Nicolaides, Associate Professor in Gas Turbine Engineering and Thermal Engines Lab, lead in the Department of Engineering and Aeronautics at the University of Patras, Greece. With a strong foundation in research, he gained valuable experience as a PhD graduate, lecturer, and later as a reader at Cranfield University, specializing in gas turbine engine performance and numerical simulation. He also served the program director of the Thermal Power Propulsion MSc course until his departure in July 2024. His expertise spans engine design, performance analysis, aircraft engine integration, engine diagnostics, and environmental impacts of civil aviation jet engines. With extensive academic and industrial experience, Dr. Theophilus aims to further develop his academic career, contributing to teaching, research, and management. We now request Dr. Theophilus Nicolaides on the stage for delivering the keynote lecture on aviation and contrails, impact, challenges, and the way ahead.
Do we have that? Where is that?
Okay. Thank you very much for this nice introduction. First of all, I would like to express my gratitude for the invitation, and it's a real privilege to be here in university and in India generally, a unique experience for me. I would also like to express my gratitude for the hospitality. I'm really feeling like home. So, the topic I selected to talk about is about contrails, which is actually quite I can say, alarming problem in the aviation. And more research is taking place nowadays. I will explain what it is, how they are formed, and actually the challenges and what we can do actually in order to alleviate the problems. So first of all, how can I change the slides?
So see.
Yes. Okay. So what is contrails? Actually these are line-shaped ice clouds. It's basically ice clouds. It comes from the word condensation trails, and it's water converted to ice. These are generated by aircrafts cruising at cruise altitudes, flying at cruise altitudes, and around 8 to 13 kilometers altitude. And there is a reason for that, because the temperature up there is quite small. So this helps this formation of ice. And yeah, okay. So these can be distinguished to short-lived contrails, so they form and they disappear, and persistent contrails, which means that they stay there for more than 10 minutes. 10 minutes is just an agreement between the scientists to define these persistent contrails. So they stay there for more than 10 minutes, and the problem is that they form these cirrus clouds. So this is the first, the only clouds that they are created by the human activity in the upper atmosphere. I don't know why it does not work. Yeah, and now let's see the formation mechanism. We can all understand that when the aircraft flies and the engine operates, it produces emissions, of course, because it is the air and the kerosene which is burning. For an average turbofan engine, this is an engine which is with a bypass ratio of 5.5, and it's basically an engine flying with A320. In 1 hour of operation, the aircraft consumes around 850,000 kilograms of air, and it consumes more than, sorry, that way. So we have a production of different emissions in the atmosphere, and the most important ones are CO2, of course. In 1 hour, this engine can produce 8.5 tons of CO2. But it's not only CO2. CO2 has, we have a good understanding about CO2. It's a stable particles. They stay there for many, many years. The other particles is of a problem, and they contribute to the creation of these contrails, ice formation. And we have, of course, water vapor, 3.3 tons of water vapor in 1 hour of flying at cruise conditions. And we have nitrogen, sulfates, hydrocarbons as well, and particular matters in soot. And soot is part of the problem. So we produce all these emissions during 1 hour of flight. Now, how contrails are formed? Of course, we have the hot water. The hot water is in a vapor form because the exhaust temperature of the engine is around, for this engine, is around 500, 600 Celsius. That means that the water is in vapor form. So what is happening? There is a lot of turbulence as well. Yeah, thank you very much. So there is a lot of turbulence as well. So the hot water mixes with the soot particles in the air as well, and there is a heat transfer process. So because we have 600 Celsius from the exhaust of the engine, and the atmosphere we have -50, -55 degrees Celsius. So immediately the vapor starts becoming, there is heat transfer, and the vapor becomes ice, liquid water, and ice. And the question is that if it remains there as ice, then in a big quantity, then we have these contrails, these ice clouds over there. So I will not talk in detail about the formation process, but more or less this is what is happening. Now, the question is how we can model these things, because we need to model these things in order to be able to predict them. That's the question. Now, modeling, we start again from the basics, because simplicity is quite beautiful in a preliminary design and the preliminary studies. So we have this very simple diagram of saturated vapor pressure of water and temperature on the other hand. So we have the saturation liquid curve with respect to liquid water and with ice. That's basic physics, and evaporation takes place. So we assume full heat transfer between the water vapor and the atmosphere, and we can start from point P over there, which is just out of the exhaust of the engine, high temperature. And we have the water vapor. And finally, the water vapor will end up in ambient conditions. So it will end up in point A. So as if we assume uniform heat transfer, we can assume that we have a straight line which connects point B and point A. When this mixing line, as we call it in this activity, if this mixing line crosses the saturation curve of liquid water here in point F, this is where contrails start forming. So contrails will form because vapor will become liquid water, and eventually, because of the low temperature, it will become ice over there in point 3. So it will become ice over there, and now the question is about the atmospheric conditions. If the atmospheric conditions is, like in this case, point A, contrails will form, but they will disappear. So we will see a very thin line, few, let's say, hundreds of meters away from the aircraft, and they disappear. So this is not a big problem, it's a natural process. The problem is when this point A is within the ice saturation curve. So we talk about ISSR region, ice supersaturated region. If these conditions prevail in the atmosphere, then the contrails will be persistent. So point A will be over there, and contrails will be persistent. So we create clouds in the upper atmosphere. In order to model these things, we follow for many years the well-known Smith-Appleman criterion. And I'm showing this equation just to give you a feeling of the models that we are using. So we have different parameters which are related with the atmosphere. For example, the emission index, the CP, epsilon parameter. And of course, we have the engine as well and the fuel. That's why I'm showing this. So it's the engine technology, which is reflected by the overall engine efficiency. This reflects the engine technology, and of course the fuel, which is reflected by the combustion heat per mass of fuel over there. So fuel and engine play a very big role in the formation of contrails. And of course, in order to model these things, we use this calculation, the slope of this mixing line, which is very simple to calculate because it is simple because we have made a lot of assumptions about the transformation of vapor to liquid. And this is one of the areas of investigation nowadays. I'll talk in a while about that. So I have explained already that what is happening and that what are the conditions of the formation of the contrails and what we do, how we can assess how we can assess if the contrails will be persistent or not. So, what is exactly the problem with these things? The problem is that, as we already know, the temperature of the atmosphere changes. There is an increase of the temperature. And I put this slide over there because it is based on scientific consensus. I like this word because there are many people that believe, no, we don't have a problem. But many scientific organizations have agreed in the same conclusion. So we cannot have doubts. Everyone may have an opinion, however, scientists should present evidences, and evidences are there. So there is a problem with the temperature of the atmosphere. And contrails may contribute to this temperature increase. And if they are persistent, of course. So this makes things more complicated. So if they're persistent and they induce cloudiness, yes, they contribute to the problem. And why they contribute to the problem? Because they create these clouds over there in high supersaturated region, which is not so rare. In many cases, we have this region in the upper atmosphere. And they create, after 10, 15 minutes, these clouds over there. And what is happening with these clouds? They absorb the solar radiation, okay? And they do not allow this solar radiation to reach to the Earth. On the other hand, from the Earth, does not allow the radiation the Earth emits, the terrestrial radiation, to escape to the universe. So they destroy this balance which exists in the globe for many thousands of years. So that's the problem. They destroy the balance between the radiation, solar radiation, and terrestrial radiation. And the problem is usually bigger during nighttime, because nighttime is the time when the Earth normally sends the terrestrial radiation to the atmosphere, while at the same time there is no solar radiation. So the balance is destroyed. And of course, So if we would like to give a better picture, we have an aircraft which is flying, and we have the solar radiation, the terrestrial radiation, and there is this change of the balance. This balance is called radiative forcing, which is actually the radiation with regards to the energy which is received and emitted to the atmosphere. So we try to quantify that through this parameter, which is called radiative forcing. And of course, the aviation is not only the only activity. Of course, we should not blame only radiation, because there are so many activities which may destroy this balance. And this makes the problem even more complex, because someone may ask how you can measure that this change in RF is caused by contrails, because there are so many other activities. But there is a way to avoid this, tackle this problem. Okay, so there are so many other activities, and contrails makes things worse in this radiative balance. Now, there is another, and of course there are many in situ measurements actually, because the technology has improved a lot with the measurements, and that helps the scientists considerably in order to prove that there is a problem over that. So here we have some measurements of the radiative forcing taken for March and May 2019, and you can see that there is the net radiative forcing is not zero over there. So this means that this radiative forcing contributes to the change of the atmospheric temperature. So there are measurements and evidences for that. Now the problem is, of course, in these measurements, and I present these different type of measurements. I will focus on these contrail cirrus in high humidity regions. Yes, they try to measure, but the problem is the uncertainty. You can clearly see that there is a lot of uncertainty. So the confidence is quite low. Okay? And this is actually a problem, because if you have low confidence, then you cannot convince people to change the policy. But this is the perfect environment for research, because with research, we try to reduce this uncertainty. And I think that we will achieve that. So uncertainty is quite big. Now, let's have some messages so far. So calculated contrail cirrus formation, yes, or avoided, is much more challenging than CO2, because CO2 is a well-known quantity, it's much more stable, while contrails is not. The other one is that our understanding is not great so far, but it is evolving. More and more standards are taking place nowadays. Yes, we are not confident to quantify the impact. Very good. This is something that we have to accept. Not confident. And of course, we try to develop metrics for equivalent to CO2, because we would like to separate CO2 with contrails. Contrails are included in non-CO2 emissions. So we have CO2 and non-CO2. Contrails is a big part of non-CO2 emissions. Metrics are, we are trying to develop the metrics similar or equivalent to CO2. However, they do have an impact. This cannot deny that. Okay, so we need to stay on this, the last statement, that they do have an impact. We need to find how much and how we can avoid these things. Now, what can we do? What is the technology that we can do, or the measures that we can take in order to alleviate the problem? I will start with the basics. First of all, there are technical means in order to reduce the contrails. These can be with the novel propulsion concepts and alternative fuels, of course, in order to minimize the soot formation. Operational means to avoid these high saturated ice regions, if we are able to predict them, because there is a difficulty there as well. So let's talk about a little bit about the technology. The technology, as my predecessors have discussed about electrification, seems to be one solution, because if you have electrified aircrafts, then you don't have soot, you don't have emissions. So probably this is a solution. However, there are challenges that have been discussed here about electrification, particularly in the long-range aircraft, because with a short-range aircraft, there is no problem with contrails because they do not fly so high. Remember, contrails form in the upper atmosphere, so we need to have this cruise altitude of 8 to 12 kilometers altitude. So short-range aircraft fly lower, no problem at all. So we are focusing on the long-range aircraft. Electrification probably will be a solution for contrails. So other technology, of course, disruptive propulsion concepts about distributed propulsion can probably alleviate the problem. And of course, the message is that there is it's an innovation area for aircraft performance. Now, contrails have become part of the equation in order to design disruptive propulsion and help the technology, so the technology to be developed in order to help the contrails. Water extraction, as we have seen, contrails form because there is water in the emissions. So what if we reduce this amount of water? And MTU has developed a facility where they have a number of components, condensators and generators. They extract the water from the exhaust and they store it in the aircraft and they divert it back to the engine and they eject water in the combustor. That helps the performance and of course the reduction of the NOx emissions as well. Of course, there are many problems and challenges there. One of them is that you store water in the aircraft, you increase the weight of the aircraft. Okay, you reduce, of course, you consume fuel, but at the same time, you have a lot of water over there. But okay, this can be a solution for the contrails as a problem. However, there are other things that we need to consider. We did a very, let's say, preliminary study to see how much water you should extract if you have a facility of this type. And we found out that you need to have more than 53 to 75% of water should be removed in order to eliminate the contrails formation. So for not persistent contrails over there and persistent contrails, as the humidity, relative humidity increases, so if we fly in a humid environment, contrails will form in a more easily way. So that means that you need to reduce the emission index of the water even further. So you need to remove a lot of water actually, and this is for kerosene. If we do the same exercise for hydrogen, then this amount can be about 80% to 91% water removal. So you need big infrastructure in the aircraft. So we do believe that probably this is not a feasible solution. Okay. Now, new fuels, why not? And I will start with SAF as well, as it has been discussed. SAF can be a solution in the problem because they have less soot particles, and soot particles is the fundamental thing, and the water, of course, where contrails are formed. So less soot particles, probably we have less contrails. And there is, the study here about the reduction of soot particles. This is a graph where it shows the soot emission index. And as we move towards sustainable fuels, these soot emissions are lower. So we expect the contrails to be lower. I'm talking about persistent contrails. And this has proven by a flight which from Airbus actually flew in 6th of June 2024. So they flew with 100% sustainable aviation fuel, and they try to investigate about the contrails formation. What they have found, they saw a considerable reduction of ice particles. That means that the water does not have so many soot particles, so it cannot form ice so easily. So we have less formation of contrails. So that was observed, that was a proof that this solution may work with SAFs. Hydrogen, yes, of course. Hydrogen is a very good, it seems to be a very good fuel, and it will help considerably contrails problem. And of course, with hydrogen, we need to consider new aircraft as well for different reasons, other challenges. So new aircraft, new design. So probably our models for contrails, of course, should be slightly different because the aerodynamics would be different. And there is one more parameter which is very, very important. There are no soot particles. Okay, so no soot particles. However, the question in scientific community is about aerosols. We will have aerosols. So what would be the impact of these aerosols? And also our concern is the emission of the index of the water, because with hydrogen, the water is 8 times more. Okay, so the water there will be much higher percentage. So what would happen with aerosols? So probably we are thinking that we will have contrails, but we do believe that they may sublimate and they may disappear. So they will not form induced clouds over there. They may be persistent, but not with clouds.
avoidance the regions where contrails are formed. And these regions, remember, is the ISSR, ice supersaturated regions. So what if we knew these regions before the flight, and we deroute the flight and we say, let's avoid this, we will fly lower or even higher, probably lower. So flight deroute probably is a very quick solution. However, there are other problems there because there is a lot of uncertainty. There is uncertainty also with our models, uncertainty with the weather prediction. The weather can change rapidly. I'm talking about the relative humidity in the upper atmosphere. So we need an aircraft to fly and take measurements. It will report this, but there is a possibility after an hour, the situation to be totally different. So the aircraft flies in the morning, it creates contrails. The other aircraft in an hour later does not create. So contrail avoidance, there are several factors which needs to be considered. The first one is that the avoidance is successful, so we do not produce any contrails. Very good. What we produce extra CO2. Why? Because the aircraft flies in suboptimal condition, probably lower. That means that L/D is different, not optimum. That means that the aircraft operate, the engines operate more fuel, more CO2. That would be the knock-on effect. But there is another possibility to fly in another route and you create contrails over there. So you fly suboptimal condition, you spend you consume more fuel, and you create contrails as well. And of course, there is an even worse scenario where you we deroute the aircraft, we consume more fuels, we produce contrails, and we found out that in the first original route, there is no contrails formation. Okay, so there are many difficulties in that related with the prediction models. So prediction models should be improved. And needless to say, how much aircraft fly at the same time. Then this is a screenshot from Flight Radar 10 days ago, and 9:26 UTC time. Actually, you can see the number of aircraft flying at the same time at cruise conditions massive. So yes, we do fly, but what would happen in the future? In the future, the situation will be even, let's say, worse. I cannot say worse, but it will be much more challenging. More aircraft. So the forecast for 2050 is, according to IATA, is to surpass 10 billion passengers. So it's an outstanding number, actually, about the traffic. And traffic would be a huge problem there. So imagine that traffic control should accommodate all these changes due to, in order to improve the contrails formation. It could be a very challenging task. So just to recap and complete my presentation, contrail mitigation strategy, navigational avoidance, yes, it's a possibility. However, the uncertainty on weather prediction is challenging. Also, our models of predicting contrails or not. Water extraction devices with a question mark over there because there are the problems in the aircraft technology. Disruptive propulsion technology, as you have seen, electrification, yes. However, need a solution in a more, let's say, future. A change of fuel, SAF, is quite, has quite a huge potential on this. So these are probably the challenges we need to face in the potential solutions. This is a good environment for research and for universities, research scientists, and the industry as well. And of course, in that, in order to persuade the government, in order to take and develop policies on these things. And this is a nice environment. The solution will come from the research organizations like your university. So, having said all these things, probably you've seen this movie, Don't Look Up.
However, in case of contrails, we should look up actually. We should always look up because that is part of our problem. And the environmental impact of the aviation is very, very important, is the key, is the driver, as my predecessors have discussed. So thank you very much for this, and I would be happy to take questions. Thank you very much.
Good afternoon, sir. Myself, Shreyas. Sir, I want to know about how formation of contact interact with atmospheric turbulence.
Atmospheric turbulence, yes. This is another factor which is very, very important because it helps mixing and the heat transfer. You have atmospheric turbulence, the winds, but it's much more important the turbulence created by the aircraft. So the aerodynamics of the aircraft can affect the formation of contrails. That's why the design of the aircraft is also important as well.
Thank you, sir.
This is another area of investigation in the contrails modeling.
Good afternoon, sir. Myself, Agam Jain. My question is, are contrails related to somewhat NCRs in noctilucent clouds? And also, apart from aviation, is there something that can lead to the formation of contrails? And one more question is that what are the ways to detect the contrails? Just like NCRs, we have imagery from suborbital flights and imagery.
The first question was about, sorry, I have not understood.
Like are contrails are somewhat related to NCL, the noctilucent clouds.
Which cloud?
NCL, the noctilucent clouds that are actually formed in the upper mesosphere, about 80 kilometers of altitudes. So are they related somewhat to it, the formation?
Yes. Well, this is what contrails are doing. They form these clouds in the upper atmosphere, 8 to 10 kilometers away, and that is the problem is when they are persistent and they stay there for a long time, and they stay there for the long time because the atmosphere helps this. It is the ice supersaturated area over there. The second question about.
So like apart from the aviation, is there anything that can lead to formation of contrails like rocket launches or something like that?
Rocket launches. Yeah. I think from the type of the fuel they are using, should not. Rocket launching. Should not. I'm not aware of rocket launches actually in the promise of contrails. Probably they can create something, but the number of rockets is not so considerable compared with the aircraft that are flying constantly. Because an aircraft can fly at cruise conditions for 3, 4, 5, 6 hours. So this is actually the problem. They can pass from different regions. So, and after that, another problem is that this cloud, depending on the atmospheric conditions, can move elsewhere to other regions. So the problem can spread actually. So I think the problem mostly is in the aviation, not in the rockets. Yeah.
Yes, so thank you so much.
Good afternoon, sir. My question is like we are more focusing towards the sustainability. So, sir, do you think the biofuels and the sustainable aviation fuels can replace the conventional jet fuels in a long way?
I think, yes, my personal perspective of that is that, yes, aviation and biofuels is the next step before anything else. Hydrogen is a little bit far away because there are many challenges, but biofuels, yes, SAFs. This is the next step actually for us in order to alleviate the problem. So for sure. And with regards to contrails, as I have presented, it has the potential to be, let's say, to alleviate the problem again, because it cannot eliminate, we'll have aerosols there, small soot particles, but the problem will be less considerable.
Okay, thank you, sir.
It was a wonderful presentation. I have got only certain observations. Number one is, if you can adaptively and optimally identify the trajectory, which a lot of work is now being done to take care of this contrails problem. And that means the trajectory can be mapped and predicted a bit, in advance, so that the aircraft trajectory can be accordingly taken up, depending upon the condition of the atmosphere at that point of time. Now, using AI, one should be able to really identify that on such and such date, time, altitude, longitude, latitude, altitude, etc., what should be the situation. So if that kind of things can be implemented, that may be one of the solutions, as you very rightly pointed out, other than alternate fuels, which surely should be thought about. Thank you.
Yeah. Actually, this is what actually the research focusing right now is to predict in a specific trajectory the weather conditions in order to check if contrails will form or not, and then avoid this specific trajectory. The challenge is to predict the weather conditions. This is one of the most important things. And of course, the improvement of contrails models, yes, this is another research activity which is taking place right now. Now, regarding the prediction of the weather, into the game, we have the satellite images. And as you correctly mentioned, AI techniques, because we have lots of data about weather. We have, of course, past data, what was the weather an hour ago, but it's difficult to predict what would happen in 2 hours. And this is actually the critical point to predict, because the aircraft cannot change, you cannot deroute the aircraft instantly, because there are other restrictions for them air traffic control. So there are many uncertainties, and AI will help considerably in this aspect. The other aspect is that we have now we are monitoring many aircrafts if they produce contrails or not. So we use AI in order to update our physics-based model. So there is a lot of work which has been taking place together with AI and satellite image as well. So yes, this can be a solution. AI and data mining will help considerably in weather prediction and prediction of contrails as well. That's all. There's one more.
Is there any study being conducted, right? Oh, say, the sustainable aviation fuel is not giving the contrails, and that, fossil fuel is giving the, contrails, right? Is there any study being conducted between the combustion pattern of these both fuels, which is causing this, the variation in that pattern?
A study of using, let's say, alternative fuels, you mean?
Yeah.
Yeah, of course. There are many studies, and actually there are a lot of experiments have been done by the aircraft manufacturing companies on that. so far the majority of the prediction models are physics-based or models based on data, so database models. We are a little bit behind on the validation and verification. And currently, what we're trying to do is to update the models with the new fuels. So that is requires a little bit of effort because the Smith-Appleman criterion is a little bit, let's say, old. It's very good. It works very well with kerosene. Now the question is, what will happen if you have a biofuel? And this is very, very important in order to combine this with the weather forecast in order to have a very good model and reliable model. And so the company and the air traffic management can know for sure if they need to deroute an aircraft or not. So there are models on the different fuels as well, but not verified.
Okay. And also, if you look at that, right, global warming contribution from aviation, right, 2.5% for the carbon, but it's contributing 4-5% of the warming effect because of whatever that you are cutting this rails and also soot and other things, right? We don't know the quantification of that 1.5% for that. That's what everybody told.
Yes.
But yes. What is the main motivation to choose this as one of the factors from your research?
Yeah, we do know that there is this change in the temperature, but we do know that contrails have an impact. Non-CO2 emissions, let's say non-CO2 emissions have an impact. And we are not so clear, there is a loss of uncertainty, what is the percentage which is caused by contrails on non-CO2 emissions. So this is actually another area of investigation in the research to develop metrics for non-CO2 emissions, which is far more challenging than CO2. We know CO2 is stable. You produce this amount of CO2, it will disappear in 30% after 100 years. So you have metrics. With non-CO2, we don't have metrics. We change the fuel, again, another problem arises. It's quite challenging area, but yeah, it's quite fascinating for researchers.
It's good to study that because, right, amount of effort and then already we are putting onto that, right? What is the effect of that? If it is quantified, it will be good to put the effort to, minimize that instead of randomly picking up. That could be one of the point we can consider your study, right? Maybe various non-CO2 effect on that global warming.
Yeah, if it is, if we're able to quantify these things and we gain more confidence that what would happen, we can establish policy to the companies the way they fly. So they will feel much more comfortable when they want to deroute an aircraft. They will spend more fuel, but they will be sure that they do not create non-CO2 emissions and contrails. So that will be a benefit for the environmental impact. Yeah.
Thank you.
Thank you very much. There's one more.
Sir, this question is regarding the research in aviation contracts. From the presentation, we understand that there are many models made and simulation work on that. Also, in situ based experimental techniques. So, are there any real-time experimental laboratories set in the ground to have such kind of study on contracts?
To my knowledge, unfortunately not. We do not have land-based applications for different reasons. The formation of contrails is taking place in the upper atmosphere. So
my question is to simulate that the environmental laboratories are there like that?
Oh yes, yes. There are many laboratories which are doing very good work on that. We have developed models where we can replicate physics-based models, data mining models, where we can relate the formation and the development of these contrails. Actually, I have been working with the deroute of flights Because one important thing is when you deroute the aircraft, how much fuel you spend, and if the deroute would be successful or not. And what is happening if you use a new fuel, another fuel. Because when we use a new fuel, of course, the deroute consequences will be different. So yeah, there are many models which are numerical models which can be developed. However, there is a lack in experimental facilities, that's true. And you can see the only experiment I presented is from Airbus. Airbus has a convenience, and Boeing, I believe, to fly and change the fuel and have another aircraft to see if they produce contracts or not. Taking measurements from the atmosphere is very important. For example, in numerical models, the relative humidity is assumed. We have atmospheric weather models where we have data from historical data. What has happened in March the previous year, for example. So we use this and we predict contrails. However, you cannot guarantee that next March will be the same in this level of atmosphere, the relative humidity. I'm talking about the relative humidity. Ambient temperature is more or less the same. Relative humidity is a big problem. And due to the winds and the atmosphere is moving, you can fly an aircraft in the morning. When it returns, it produces contrails. When it goes, does not. It is because of relative humidity. Thank you. Thank you very much. Thank you.
Thank you, sir, for introducing to us a topic and a problem that most of us are ignorant about. Now, I'd like to invite our conference chair, Dr. Prashant GK, to present Dr. Nicholas with a token of our respect and gratitude.
Good afternoon, everybody. We are, in fact, currently very running a little off schedule. So I am very apologetic to Professor A.M. Pradeep sir. I would first request everybody to have the lunch currently, and followed by the lunch, I will be arranging for the session for the Professor A.M. Pradeep sir. I am very sorry, sir. I'll accommodate that. Thank you, sir, for understanding.
How this computer being there, connecting from there? Because you know that, sorry? Connecting the computer from there is possible, right? From the list. It's better you do that instead of settling that, right? Maybe next session we can plan that. We can operate from there. Maybe some video clippings maybe there play in that, right?
Charge. It must be this one.
Yeah.
Is this one? Yes, thank you. Thank you.
request each of the speakers to take maybe 3-4 minutes and give their views or perspective on this topic. And then we can also have questions. Of course, I'll have a few questions from my side, and then we can open it up to the audience. And because this is supposed to be a discussion session, it's not a monologue. So I'll request each of the panelists to give their inputs on this topic to begin with, and then we'll take it forward from there. And hopefully at the end of the panel discussion, we will have some key messages that we can carry back home. We'll start with Dr. Muniappan, please.
Thank you, Mr. Actually, right, so synergies, so basically Dr. Muniappan, right, you are also last addition to this for the discussion. Anyway, we can take it up, not a problem. I already worked in both in aeronautics and also aerospace. When we did the first EduSat, right, the micro satellite from university side, right, university is the first company, first university made a satellite, and that is launched in the, our Sri Space Station. And part of that, that is a very micro satellite that is called actually. So when you come to the right synergies in aeronautics and astronautics, advancing integrated flight technologies. So when we say like it's a multidisciplinary, subject, as right, even Dr. Frank told in that keynote session, and also if you look at the aerodynamics, structures, and the avionics, right, and then your that data link is for the RF to connect to the ground, and the ground data terminal, which is connecting your the system from the your EDT, the air data terminal to the ground data terminal, and also like the any kind of payload which is carrying. The synergy, if you take any kind of the aircraft which is meant for the commercial domestic application, whereas for the military application, it is going to carry a payload. Payload could be like that camera or the weapon. These are all the different kind of payload. When it comes to that is in the aeronautical front. When it comes to the aerospace, astronautic space, right, there the payload could be the satellite, or if you any kind of astronauts which is who's traveling to to the Mars or the different the moon mission, right. So the if you look at that, right, both are the quite the similar in nature in that kind of the list of systems primarily being there in the both the aeronautics and then astronautics or the space platform. Only difference is that propulsion system. Propulsion system, right? Here we spoke about the the different sustainability in the aviation there, wherein we talk about the fuel, the fossil fuel, wherein in the space it will be a different solid rocket or the plasma rocket, currently the ion rocket, whatever ion propulsion, whatever being currently worked out, that will be totally the different. But that is all like the kind of when we look at that overall, here's the it's very, very important to have the every system working precisely, the integrated system, starting from like if you look at that one of the launch in the last minute stopped in the Sri also due to the smallest of glitch in the the fuel tank leak or anything, right? It should be like an integrated system, should be everything working together to give us energy to have that malfunction free system to work as a whole. That is one of the key thing one need to consider. So for that to do that, we have to follow system engineering approach. System engineering approach means like there is a different function will be working independently. For example, propulsion system is different, structures is different. They then if you take the aviation systems, it's totally different. It's not the independently one can make to work the aviation system correctly well. It has to be come from the system engineering approach, wherein right everything has been synergetically working well to beat the end mission. Otherwise, right, everybody tell me actually I'm currently working on the drones. Okay, drones, I'm taking care of the complete system engineering lead, that. So what happened, right? They say that all the requirement given in the one line from the customer has to be, categorically divided into the multiple, the subcategory requirements, what is the kind of mill standard or mill ATG, what is the kind of environmental test requirement it has to undergo, certification has to undergo. Every subsystem has to qualify before we put into that. That way, right? So that is the one of the key which we need to focus to make the complete, the integrated flight system working flawlessly to the mission. Either it could be a aerospace, the domestic application, or the defense application, and also in the space applications. Yeah.
All right. Thank you very much, Professor Ray.
A very good afternoon to all of you. Hope that you had a very nice lunch. So this is a very, very important topic. That is, we have to find out, number one, say the synergy between aeronautics and astronautics. I'll just tell you a small evolutionary story. Dr. Kalam, during 1970s, he was the director of Satellite Launching Vehicle, SLV. SLV-3, that was the first Indian indigenous satellite. And the satellite launching vehicle is the first indigenous launching vehicle from Vikram Sarabhai Space Center, from which our distinguished panelist, he was there for last so many couple of decades. Now, Doctor, it was a wonderful mission, and in late 70s, in which year? 76, 77, 80. In 1980, it was a grand success. Imagine India being a country in 80 means 45 years back, while we really didn't have anything. But VSSC Trivandrum, they made it, and that was a grand success. Now, what did they do? Suppose there are a lot of bridges and a lot of gaps, in my opinion, even in our academic curriculum, whatever is being taught to the students. For example, I can tell you that from a student's perspective, I went to VSSC for a small internship from IIT Kharagpur. And there I found that the whole, I am not from aerospace or aeronautics department, I was in electronics department. But I knew, because we did a lot of projects with aeronautics department at IIT Kharagpur jointly. Some of them was, those remotely piloted vehicles. The electronics part we used to design, and the vehicular part, aerospace department, they used to design, and then we used to regularly test them. And completely, a system which even in 1980s we imagined that how it could be developed. Now, similarly, I found that they had a very strong instrumentation division in VSSC. So I inquired that in IIT Kharagpur, we did not have any specially such strong instrumentation division at IIT Kharagpur in aerospace department. So immediately after coming back, I had given the department, I was also a student, but I told some of my friends and also to the head of the department of aerospace engineering department that whatever I have observed, number one is, for example, whether it is in aeronautics or in aerospace. Aeronautics means your aircraft will fly within the atmosphere. And once you talk about astronautics, it can go above the atmosphere, and then you can play with a lot of environments which are in the space, as we say, much above the atmosphere. So naturally, there are a lot of synergies and a lot of similarities and a lot of things which are new. That means, suppose the vehicle re-entry system, when the satellite is coming back onto the Earth. So that means it is coming from one environment to another environment, which is inside the atmosphere. Lots of things happen out there. So you have to understand very properly the interface. Now, whatever it may be, both the systems, they need very good sensors. I can give you some example. VSSC Trivandrum in 1970s, that is almost, 50 years back, they had developed some accelerometers. And they had claimed that their accelerometers were better than the accelerometers which were developed by Skylab. Those days, the Skylab project was very, very prestigious project all over the. So I used to go to I was in that CGI, Control Guidance and Instrumentation Division. That was that gold building. And yes, so that was I really used to have and I did some controls job because in 3-4 months internship you cannot do much, but then I continued. So you have to have a very good idea and a very good laboratory on control system. Control system means, for example, in both the cases, the control system means not simply the linear control which is being taught in our academic curriculum. Nothing is linear in the world. The control system is essentially a non-linear system, number 1 point. Number 2 point is, it is an adaptive system because situation is continuously changing. So, and then in today's parlance, we say that everything should be optimized. So the control system also should be an adaptive and optimal control system with lots of nonlinearity involved in it. My dear students, please try to go through some of the important aspects of nonlinearity, some of the important aspects of how do you design an optimal system and how do you design a system. Adaptive means what? For example, something you are going to control whose mass is continuously changing. The rocket is moving up. The mass is continuously changing. Environment is continuously changing. So it has to adapt itself. So this is one of the things which even in academics, in my opinion, one has to understand. You may not know or you may not do a lot, but at least you should be aware of the scenarios, what is happening and what you are going to face in future life. About, as I said, all kinds of sensors. Sensors are the backbone of any engineering discipline. And in my opinion, I would like to, request even say VIT. I mean, wherever I go, I tell them, have a completely common sensor laboratory for all the students of the institute, whether he is from electronics or mechanical or aerospace engineering. There should be, you must be aware of how a sensor works, and associated with the sensor, the first thing is from the sensor data is coming. Now, what do you do with that data? So it's a wireless. In today's parlance, we say that data moves through wire. I mean, there's no wire. So it's a data wireless communication, and then it has to be stored somewhere. So it should be stored either in a, for a big system, there should be a good computer system. Now in today's parlance, we say that it should be stored in some digital signal processor, or maybe that in some cases, some microprocessors or microcontrollers, whatever it may be. So you should know that, okay, how such a system works. You need not design that, because being an aerospace engineer, nobody wants you to design, but you should have a clearly good idea about the sensors, the associated electronics and all. Second important thing, in my opinion, the synergy means, let me tell you the gaps which at least I have observed. Number 2 is that after making that satellite launching vehicle, Dr. Kalam was a project director, And those days it was a grand success, as I said, 80 or 81, it was finally launched. And then after that, from space, he went to Hyderabad. So he became the director of DRDL. And those days, somehow I had I was fortunate that we had a lot of projects with defense. And through those defense projects, he used to chair the session in the evaluation committee because they used to give us projects to IITs like say IIT Bombay, IIT Kharagpur, IIT Bangalore and all. And then we used to do those projects. And in these projects, we have to present that whatever we are doing. A very important thing was those days, in 70s only, they used to have a balloon board system. Balloon board systems are not that costly. You need not do anything. You purchase a very good quality. There's some special type of material. So here in VIT and Bhopal, you can design, the students can design a balloon system. Okay. And they used to have a sounding rocket, and every Tuesday or Saturday they used to fly that. I remember in Trivandrum. Every Wednesday, yeah. That was it's so nice to see, even from a student's perspective, I'm saying. Now, a balloon board system, you can design so many things. That means how to make, and because you will get a complete idea about how the aircraft or a airspace vehicle is designed, controlled. Balloon board system means you should be able to control it. There should be it's like a drone, but advantage is that it's very light. Inside the balloon, you can keep lots of things. You can even use that balloon to lift something from underwater. So that aeronautics now can be, or aerospace can be linked with underwater robotics. Suppose there's something, there's a drowning case inside the sea or ship. So you can lift it up. What is needed? In every case, out of all these sensors, the most important sensor is different types of cameras, optical sensor. These cameras again should be of multiple number of frequencies. So they are known as multispectral cameras. So what they do is, in case of, for example, the satellites, we used to work with a special type of multispectral camera, which was a 7-band camera, and that satellite image was known as Landsat. Even today you can get the Landsat data. Lots of people, they work with it. So even in your camera, in your balloon system, you can have a camera. Have the photograph of your Bhopal, your entire campus, and then have some computer science student to do the processed image. Because after all, we were discussing so many things in the morning. Some of you said that, okay, whether we can detect certain things from the satellite image. So here it will be an aerial image. You yourself can design an aerial imaging system. And then from those images, somebody can do the image processing of whatever you are looking at. And then from those processed image, now again, it can redirect some of the functions so signals can go back to the original value. So lots of interesting things are there which you have to learn. Second important thing, as was mentioned, being a teacher. Sorry, in fact, teacher needs to keep track of time. Excuse me, sorry, yeah. We'll continue later.
Yes, so good afternoon. So here we are talking about synergy of aeronautics and astronautics, as Professor was telling. In aeronautics, we use the atmosphere, and in astronautics, we somehow try to cross the atmosphere. There are very starking changes in this. For astronautics, at least in the launch vehicle community, aerodynamics is a nuisance. So anything you take on aerodynamics is a nuisance, right? From the lift-off to the injection, there is a drag loss. It creates unsteady loads. It creates buffeting. It creates acoustics. And it creates control structure interactions. So all those things are unnecessary things. It is like in our society, you have lawyers, you have policemen. Are they required? Yes, they are required because there are nuisance creators and you have to control them. So the task of an aerodynamics engineer in the longevity community is like a policeman, technical policeman, to see, yes, this is the nuisance it is going to cause. But then what are the two important, game-changing technologies in which this synergy is important? There are two things which comes to my mind. First thing is point-to-point transportation. Like I want to transport a tank from one place to another remote place. How do I do it in the minimum possible time? There was a slide which was put by the first speaker. Minimum weight, no cost, no fuel, and clean air. There's something like that. So we have to minimize all the things. So the whole process is, how do you, with minimum energy, how do you get the maximum payload? So in this regard, what you have to do is you have to somehow cross the atmosphere in a very fast manner and then re-enter the atmosphere and come very precisely. And that's why the importance of sensors, which Professor Ray told, it becomes very, very important. Sensors are very, very, because they are the eyes and ears of the the control systems. The navigations, guidance and control will fully depend on the sensors. So one thing is, we should develop a technology in which I will be able to do point to point. So in this, what is important is the retro propulsion, which Elon Musk does. You go up, then come down very slowly and land. So for that, you require a technology called the retro propulsion. So with these two, you will be able to manage this. And another thing is, how do you make the transportation very fast? That is through the hypersonic transport, that is by scramjets. Like, we are now working on this. ISRO also is working on that. Suppose I am able to have a scramjet engine, which goes from, let us say, Mach 6 to Mach 7. So it is something like the same, travel which you are traveling from United States to Delhi. In a scramjet, you will be able to do in minutes. In 20 minutes, you will be able to come and land here. But there are a lot of challenges there. In the case of a scramjet, the aero propulsion interaction, it is an airframe integrated scramjet, which means that you should have minimum drag and maximum thrust. The T minus D should be positive. So that is a very, very challenging thing, because the whole thing comes into picture, and you should be extremely sleek. Even small projections also has to be avoided. And you should get the best performance for the scramjet engine. And the scramjet engine is not a joke, because it gives a lot of heat. Then you should have a good heat disposal. In fact, one of the reaction engines in UK is working on this particular technology. They have been working for so many years, but still a breakthrough has to come. So this is another game changer. Will you be able to do a scramjet engine so that a transportation system is scramjet engine? Because people are working with missiles, but a transportation engine is a real challenge. So in this regard, the synergy between aeronautics and astronautics is basically you use the cross the atmosphere as fast as possible with minimum losses, and enter the atmosphere and use the atmosphere and land safely. So in all these two technologies, this is very, very important, and there are several such important aspects in which aerodynamics, flight mechanics, the aerothermostructures, controls, sensors, materials, very, very important. Materials is a very important technology. We have to have a proper material to withstand those very high temperatures. Because when we re-enter the atmosphere, the whole thing is changed. The oxygen dissociates, the nitrogen dissociates, then you'll have the nitrous oxide forms NO+, and the electron cloud will be there. There will be communication blackout. So many issues are there which has to be tackled. So it is a challenge for the entire, aerospace, the engineering community, not just the aerodynamics or the flight mechanics people, but the entire system of people. So this is a very great challenge, and I'm sure that we'll be proceeding towards in the future in these directions. So thank you. This is my brief on this.
Good afternoon, VIT Bhopal. I am the last speaker, but last but not the least, and I think I am the younger one in this distinguished speakers. So first of all, actually, these organizers are very, very much smart. After lunch, digesting the good food and digesting the lecture of Dr. Pradeep. So what they did a panel discussion so that you can little bit settle down, and after that you can easily digest Dr. Pradeep lecture effectively, right? And since I belong to a fraternity as Dr. V. Ashok has already told now, he belongs to aerodynamics, means I can say from aerospace background, BSSC. Fortunately, I was also working there, but soon after I got transferred to SEG Ahmedabad. I think that with management has given an opportunity to sit with Dr. Ashok, so that the synergy between the aerospace and aeronautics can be the bridge they can get. Because I belongs to a fraternity where the payloads are designed and developed. We are actually the person, I belong to a center where these all payload sensors, transporters are designed, right? So that the eyes or nose or your skin, what your body is having, same thing actually we are designing for the spacecraft. So this topic, bridging of aerospace, is basically both of them are sitting in a same platform now. So we are actually bridging the gap. And as far as the space science is concerned, for my definition, for simple space definition is basically space means no air, no repair. So it means what you want to do it now, you have to do on the ground. Either it is revalidation or either be testing, validation. What you want to do it, you have to do it on ground. That's why the typical example last year, 2023, you can see that we have successfully insertion or successfully soft landing on Chandrayaan 3 on the south pole of the moon, and we become the first country in the entire globe or world who has soft landed on the south pole of the moon, right? So this shows that the capability of I can say the person who is working in aeronautics and astronautics field, they have precisely planned the mission, and as per the mission requirement and goals, now we have achieved this. So that's why the 23rd August 2023, as I mentioned last year only, that International Moon, I can say that now we are celebrating a National Space Day on that day. And this shows that the capability of all Indians, means all Indians are cherishing, but at the same time, all scientists, those actually behind of this mission, that is, once his mission is successful, then it is a cherishing, I can say, cherished moment for all of us, especially for all Indians. And so going to in a deeper way, anyway, we have discussion by one, but to be very much simpler, I can say, in another way, I can say, rather than going to technical word, if you see that more than the 50 countries, means out of that, if you count, more than 200 nations are there, registered nation in United Nations, right? More than 200. If you take the example of Paris Olympic, near about 203 countries have participated in the Paris Olympic. Out of that, if you see 15 countries, more than 50 countries having stars or moon on their national flag, right? If you see their national flag, so they have more than a stars or moon or something in their national flag. After 23rd August 2023, we become the 4th country in the entire world whose national flag on the moon, right? So there is a drastic technical difference. So that's why I don't want to tell you what difference or what we achieve from this mission. So that's all from my side.
It's very well put. I didn't really think about that flags, but I think that's a very nice take on this. So I think in the interest of time, since we're running slightly behind schedule, we'll take a few questions from the audience and then we can have a discussion based on that. So audience, if you have questions, please bring it up. If you need a mic, you can borrow this.
Good afternoon, everyone. So, sir, as discussed on the topic, I just wanted to ask a question that what are the most promising areas of harmonious integration in which the aeronautical and aeronautical systems would work?
Can you repeat that question? Repeat the question.
Yes, sir. So, what are the various methods in which harmonious integration of aeronautical and aeronautical system would work?
speak right, for example, we need in the aerospace or the aeronautics, right? There are the few elements to them. For example, first is the primary structures, then your communication system, your control system, and then payload, okay, and then your ground station system. All these things are kind of right harmonious, so all are kind of unique, except that right whatever Dr. Ashok told regarding other than that going back to the space, coming to the re-entry, right? Excluding that parameter, remaining things already kind of same. Whatever I was telling about the system engineering approach, right? We have that right. The many systems which are all common in nature. So because if you study that, right, because most of what other than that, right, whatever that going beyond your atmosphere for the escape velocity, other than that, it's almost like the system wise same, starting from the materials for the airframe, and then your communication system, transponder, and then the receiver, and the avionics control systems, and then your payload, like it's like any other kind of sensor, ER sensor, EO, electro-optic, or infrared sensor for the night missions. These are some of the kind of harmonious synergy between the both astronautics and then the aeronautics.
Thank you, sir. Good morning, sir. My question is regarding re-entry of hypersonic vehicles. So, in that you mentioned that aerodynamic heating is one of the major problems in that. So, which material is currently being tested for it?
No, there are two types of material. One is the ablative, other is a non-ablative type called hot structures. So ablative type is is where it consumes itself and then it survives the heat. But the disadvantage there is the shape gets changed. Okay, so very high heating and all, what you do, you go for ablative. But in the case of things which have to retain shape, for example, we have a reusable launch vehicle technology demonstrators. Wing leading edge has a very high heating during re-entry. So that has to be like carbon and things like that. So there it has with special coatings. These are some of the advanced areas. Even making such a technology itself is a very new thing. And in India, we are doing for the first time, and with all those coatings at very high temperatures, it should be standard. So both types of materials are being used. One is carbon type of this one, and another is carbon phenolic, silicon phenolic, where the ablative type of materials are there. So both types are used.
And sir, what about using nanofluids for heat transfer?
Those things are research topics. Yes, it is. It can be studied. But that is also another. That's active cooling you are telling. It's active cooling. I am talking about the passive methods of doing it. So that nanofluids will be useful for the scramjets, where there is an active cooling is required, and that is also an emerging area in which we have to have optimal heat transfer so that the hot structure is getting the temperature is maintained.
Okay, sir. Thank you, sir.
Good afternoon, sirs. My question is, as Ashok sir said, in SpaceX they land slowly. And as Ajoy sir also said, that sensors are very important in every field. So do you think that if it was possible to have sensors that control the speed of space vehicles installed on any space bodies like planets or the moon that has a surface, it will be easier to have soft landings and be able to have manned missions in the future on those space bodies?
Currently, what is preventing us from doing a soft landing in like what SpaceX does is not really the sensor. Sensor technology we already have. But what is required is retro propulsion. That is, you should have a throttling system. That is, the propulsion should be able to vary its thrust. That throttling is a very, very important technology. We have to a certain extent, of course, we did that for our Chandrayaan, Chandrayaan 3 lander. So similar such technologies need to be done for the our recovering the boosters also, which the SpaceX has. And they have multiple engines. So the advantage is, they will switch off all the engines, and whichever engine is required only they need to perform. So such multiple engines also need to be done. So now we are working on the LOX methane engines. That is, there's a next generation launch vehicle is another project which is sanctioned by the government of India. And there we are going to have 9 such engines, LOX methane engines, which will be able to recover these boosters.
Okay, thank you, sir.
Good afternoon, sir. So what are the potential future directions of developing cryogenic engine?
See, cryogenic engine, now we are going for, cryogenic engine, the disadvantage is we have liquid hydrogen, liquid oxygen. Now, liquid hydrogen, is very massive. You have to, and the temperature is very, very low, 20 Kelvin. So it is not, very optimal thing. And so what we are going for is semi-cryo engines. Semi-cryogenic is, one is kerosene, another is LOX methane. So the semi-cryo with kerosene has soot and other formations. Okay, today morning there was a discussion on whether this, even that, contrail, the question was asked. So only the cryogenic engines, semi-cryo only will have such, but there are very, very few only. So, so basically the direction of this is semi-cryo for the first stages, where the payload ratio, because first stage is not doesn't convert much into payload. But whereas if you the last stage, 1:1, Tsiolkovsky's rocket equation, you will be knowing about that. So there the cryogenic engine technology is there. But now itself the cryogenic engine technology is in a really matured stage, and we are to now graduate to the LOX methane engines, so which will have a not as good as a specific impulse as a cryogenic engine, but much better than solids. So that is the direction in which we are going to work.
If we consider in a sustainable way, hydrogen after combustion, hydrogen oxide will form a cloud. So basically, it is more reliable. We can.
No, hydrogen, the in a cryogenic engine, your water vapor is the output. So the things, the water vapor only comes out. But then the launch vehicles are not like aircrafts. Where today it showed that some 10 days before, what is the number of flights were shown in this one. Launch vehicle is not that much there, and it is almost in the outer space also. It is not there in the region of troposphere. So all this climate change and other things, the launch vehicle is not going to play a major role as compared to the aircraft.
So if we consider that, if we try to fix a cryogenic engine in a place, does it work that way?
No, see, specific impulse. See, airplane is very good because the air breathing engine has a very high specific impulse. Specific impulse of air breathing thousands, whereas cryogenic engine is only 452. It is not because cryogenic engine is because you are carrying oxidizer with you. There you don't need to carry oxidizer. Oxidizer is available in the atmosphere, so you make use of that. So that's what the aircraft does. So that's what we are planning. Our scramjet engine we are planning so that because 85% of the energy is wasted in overcoming the atmosphere, for which we have to carry the oxidizer also with us. So that we are trying to see whether we are able to use it or not. But then we also have to, we cannot cruise in the atmosphere. We have to somehow cross the atmosphere as early as possible. So within that time, we should gather that trust and then later on use it for taking it up.
Thank you, sir.
So I think maybe one last question and then we can.
Oh,
sure.
Please go ahead. I had a doubt regarding the placement of space mission planning in the launch vehicle design. Which happens first, or whether is launch vehicle design and payload design happen first, and then space mission planning, or is it the other way, or do they happen in tandem?
Okay. Now the question you are asking is, how do I place my launch vehicle capability? Like for example, next generation launch vehicle. We had a Chintan Shibir in which what should be our future, and we call all people and we discussed it. So first thing is we get the inputs from the commercial things. What is the projection of the next 10, 20 years, 30 years? What will be the satellite technology that is required? Because we have nano satellites coming, then you have whether big satellites are required. So then we decided that we should be able to modularize. That is what we should be able to do is we should be able to take anything from, let us say, 6 tons to something like 35 tons, and you make it module thing. So it should be one launch vehicle in which we should be able to scale and build and even take man to the moon. So that's why we have done recently a docking experiment. So what we are going to do is not a very big launch vehicle like Saturn to take it to moon, because that's it's once in a while only you get, and it's not very cost effective. So what we are going to do now is to have a next generation launch vehicle which will also take man to moon, which will also do the 6 ton to 12 ton and then 35 tons to Leo. So it will do several such operations in just one launch vehicle. So that is why we targeted upon that particular thing, in which we have only the first stage that is recovered, so that we can maximize the because that around 60 to 70% of the hardware cost is recovered in that. So that way it was planned.
All right. So I think in the interest of time, we need to wrap it up here because we're already behind schedule. And I should also be giving a talk after this. So, and the sessions are supposed to begin. So, Dr. Prashant, I think you need to manage that as well. So, I think we will wrap it up in just making a few remarks. Maybe one of the panelists can sort of give some remarks on, based on the questions that they posed. And much of it, I think Dr. Ashok himself answered.
Okay, so I think this synergy of aeronautics and astronautics is really essential for the future progress in this aerospace area, in which we should combine the technologies of both the airplane technology and the rocket technology. Should be in hybrid technology, so that we can make transportation faster, cheaper, and more cost effective. So that's there, and it should also more safer. So I think it is possible. Only thing, there are some critical technologies which need to be taken care, and it just is not just one engineering branch. It covers entire engineering branch. In fact, all branches do come into picture here, including the computer science, because we also use a lot of computers for solving the nonlinear Navier-Stokes equation with high performance computers, which you had mentioned, and we use GPUs and hundreds of GPUs, and still we are not able to do a direct numerical simulation of the entire aircraft. Which is a holy grail, which you call, which requires billions and billions of cells, and it's very extremely challenging. Now the computation part, the numerical part, and without just no turbulence model, it just comes out. So it's very exciting, and I think the whole aerospace community can be very happy that there are a lot of challenges ahead.
All right. I think on that very positive note, may I request the audience to please thank the panel members. It's not often that you get to see panelists of this stature on one stage. Thank you so much. So I would like to request all of the dignitaries to wait. Thank you, sir. Your discussion was very fruitful for the whole audience. Now I would request our conference chair, Dr. Prashant GK, to give a token of respect and love to all of the dignitaries.
Next, we proceed on to our fourth keynote of the day. Professor A.M. Pradeep, head of the Department of Aerospace Engineering at IIT Bombay, is a leading expert in aerospace propulsion and turbomachinery aerodynamics. Holding a PhD from IIT Kanpur, his research spans axial flow turbomachines, flow control, and turbomachinery for organic runtime cycles. He has authored over 65 journal papers, 93 conference papers, and holds 4 patents. An award-winning educator, he has mentored numerous PhD and master students and led research collaborations with DRDO, ADA, Siemens Energy, and Pratt & Whitney. Dr. Pradeep is also an active member of key aerospace organizations, serving as chairman of the Aerospace Resource Panel and a board member of the International Society for Air-Breathing Engines. Through his leadership, he has established cutting-edge propulsion research facilities at IIT Bombay, driving innovation in the field. Now, we request Professor A.M. Pradeep on the stage for delivering the keynote lecture on effective inflow and surface irregularities on axial compressor performance.
So, good afternoon to all of you. And firstly, let me thank Dr. Prashant for scheduling this talk after the panel discussion. So I don't have to take the blame for any of you dozing, because I didn't see any of you dozing during the panel discussion. And I hope I can keep most of you awake during my talk as well. So I have set my timer. I've promised Dr. Prashant I will not take much time, to 15 minutes. So I'll try to wrap it up in 15, although I had planned for a little more than that. So the topic I have chosen here is something that those whose names are listed there, my students, they've been working on this, and I'm part of a team who work on this very interesting topic. And I was trying to make a connection because the conference is supposed to be on sustainable aviation, and what I've written on the slide as title of my talk doesn't really sound to be something that has to do anything to do with sustainable aviation. I will try to make that connection as we go along. So let me also acknowledge some of the people who've been funding our World Defense Research and Development organization, DRDO, specifically GTRE, we've been working with them, and Science and Engineering Research Board. They've been funding some of our work. So I'm going to talk about a little into details about why this topic is important. At least that's something that I would like to think that this has a relevance in the context of sustainability. And I'll make that connection as we go along. So I'm going to talk about 2 aspects which affect the performance of a gas turbine engine. Gas turbine engine is the essence or the heart of an aircraft engine. And there are a few aspects which seem to be very important in terms of affecting its performance. And I've picked up 2 aspects which our group has been studying. And we would like to think that this has a significant role to play in terms of performance of the gas turbine itself. And what are these 2 points that I want? I don't want you to read through the slides. These slides will be made available in case you're interested. But the 2 points are, I'll explain what I mean by fouling of a gas turbine engine. So let me go back. Oops. So if you look at this last point, fouling is basically a combination of inflow non-uniformity plus surface irregularity and so on, deformation of the blade surface, especially the compressors. Over a period of time of operation of the gas turbine, the blades tend to accumulate dust and grime due to its exposure to adverse atmospheres, and that leads to what is known as fouling of the blades. And this is sort of inevitable because as years progress, as hours of operation progress, the blades are going to be fouled.
And this is going to have a very significant effect on the performance of the engine itself. And that is why we are interested in this. And because the performance of the gas turbine deteriorates, it is going to function at a level which is significantly lower than what it was designed to be, which means it is going to consume more fuel and therefore emit more than what it should be. And hence this connection to sustainability, if I may so. So if you look at this schematic, again, don't bother to read the slide, the bullets on the right hand side. This is how one would expect the airflow to be when the engine operates in its so-called nominal conditions, and when the engine is operating at different levels or extreme levels of angle of attack or side slip, it is going to experience non-uniform flow going into it. And that has a significant effect on the performance of the engine in terms of efficiency and performance loss. So that is the first effect that we will study. The second more significant effect is what you see here again on the pictures. You will see the blades of the compressor. These are the compressor blades, which over several years of or several thousand cycles of operation have, as you can see, they appear to be fouled or degraded in terms of their appearance itself. So this leads to about 2 to 3% output loss when operating under design condition, and substantially higher when it operates under adverse conditions, about 15-20%. And all of this has been documented as well in literature. So because this is unavoidable, this is something that is going to happen over a period of time, what we can do about this and try to see how we can improve the performance or not allow the performance to degrade beyond levels that it should is essentially what I will try and talk about. So again, from the literature, this is a comparison. This curve here, if you see here on the top left corner, y-axis is power output. I'm not sure those in the back can see this. Y-axis is power output and x-axis is operating hours. So this red curve indicates the degradation in the output due to fouling of the compressor blades. So as blades operate, there's going to be deposition of dust and grime on the blades, leading to a drop in performance. This is a brand new engine, which gives 100% output. And after about 6,000 hours of operation, it's down by about at least 5 to 6%. And that is a significant performance loss from the engine. And in terms of this characteristic that you see here on the right-hand side, bottom corner, the blue dot that you see here, this is a performance characteristic of a compressor. Again, I'm not going into details of what this means. Y-axis is the pressure ratio or output of the compressor versus the mass flow rate on the x-axis. This is what the compressor should have been. A fouled compressor tends to have an operation which tends to go closer to what is known as the surge line or the instability limit of the compressor, which is definitely not something that an aero engine should be operating at. So here is a schematic of an engine which I'm going to talk about, just a representative twin spool engine. This is a bypass engine that we've all seen. All the commercial aircraft would use a bypass engine like this. So we're going to talk about 3 of these components. What is shown here in the front is the fan. When you board an aircraft, this is what you see, the fan of the aircraft. And following the aircraft are 2 streams of air. The one in the blue is the bypass, the cold flow. And the one in the red is the core stream, which actually goes into the combustor and the turbine and so on. So this fan flow is something that goes into the compressor, the booster, or the HPC through a duct that is also marked here. So what we have tried to study is if the compressor or the fan blade has a degraded performance, how is that going to carry forward to the downstream components, and what is its impact on the overall engine performance? So that is the gist of what I'll talk about in the rest of the slides. So there is a close coupling between the operation of the fan because the fan is the one which is providing the flow to the booster and therefore to the combustor and the turbine. So I'm going to skip slides in between, so please bear with me. I had a lot more slides than what is required for about 12 minutes. So this is a schematic of the configuration that I will present here. I have used fans and other geometries which are openly available in literature. The ones that we actually studied, unfortunately, I'm not in a position to present here. So we'll talk about a fan, which is a famous NASA rotor 67. There is a lot of data available. It's open literature domain. So this is a fan geometry that we studied to begin with. And there is a compressor duct, which again, there are standard geometries which are available in open literature that one could work with. And the booster is again a NASA rotor 37, which is a smaller sized transonic compressor blade. So we are trying to understand how the flow from the fan, when it is operating under off-design conditions, gets transported to the booster, which is right here, through this duct. And we've also done some redesign of the duct, which can possibly minimize this, the adverse effects. So I'll skip this validation part, etc. Maybe Dr. Ashok will have a lot of questions on that. I'll skip that because I don't want too many questions from Dr. Ashok on this. So just a point I wanted to highlight here. When we started imposing roughness on the blades, some of the commercially available solvers, which again I was having discussion with him earlier, unfortunately, the way the commercial codes capture roughness is through a very simplistic modeling of roughness. And therefore, when we try to match CFD with test data with roughness, the match is reasonable. And reasonable is in italics in red. So you could look at it either way. Either one could say it is not matching at all, but this is what most literature also gives. You can see the differences here on this slide. They are reasonable, quote unquote. So difference is about between 3 to 5%. So when we look at let me talk about what's on the right hand side here. So this is the duct geometry that I just showed in a few slides earlier. So this duct is drawing it's getting its air from the fan, which is upstream. So we have tried to see how that impacts the duct performance. So if you see the duct here, the region in the red is basically indicating a large region of flow separation, which is going to adversely affect what comes downstream of this, which is the booster or the compressor. So what we have, and it sort of becomes worse in the presence of roughness or distortion. So you will see that this has a worse performance than this. This was with uniform flow. With non-uniform or distorted flow, it sort of worsens. And that has led to about 20 to 30% pressure loss over and above the pressure loss which the booster already had. So how do we minimize this? So I will skip some of the unsteady flow features that we obtained from this side in the interest of time. So what we tried to do was to see if we can minimize this region of separation by redesign of the duct. It is very much possible. One could do a simple optimization exercise, minimize the losses that the duct itself is going to produce. And when you look at how the overall system, which is the fan, the duct, and the compressor behaves, an optimized duct itself can improve the performance to about 40% reduction in total pressure loss just by changing the duct geometry. So again, I'll skip the animation in the interest of time. The other important aspect, when you look at the fan at the front of the compressor of the engine, most of these fans operate at transonic speeds, which means the tip of the compressor is going to have shock waves, which are seen in some of these in the later slides as well. So when these blades have an additional aspect of surface roughness or fouling, the shock structure for which it was originally designed begins to get distorted, and that significantly affects the stability characteristics of the fan. So for an aero engine, which has, let me go straight to that. So this is the leading edge of the transonic fan. And if you look at it carefully, you will see these shock waves at the leading edge of the fan. So these blades have been designed to have these shock waves at the leading edge for a very specific reason, because that's how the fan is going to produce the power output. Now, when the compressor blade is fouled, that is, it has roughness effects or thickness change due to operation, the shock structure that you see here is not going to be at the location for which it was originally designed. And one of the significant outcomes of this is that if the shock is not at the location where it was supposed to be, the compressor or the fan is likely to sort of move closer to the stability limit, which is basically the surge of the compressor. So one of the problems associated with gas turbine, aero gas turbine engines is that as you throttle or reduce the mass flow, the engine, basically the compressor, goes into its instability limit and causing the whole engine itself to surge. And that's a major problem for the engine operation itself. So due to fouling, one would start seeing deviations in the shock structure of the leading edge. And that is a major contributor towards reduced stability margin for the fan. And therefore, the engine operation itself is going to be adversely affected. So I will skip again some of this because I'm already close to my time that was allotted. So what we're trying to do now, we have looked at the performance of these components individually, that if you have fouling, the performance of the fan is going to be severely affected. Now, what if you combine these components together? You have the fan which has fouling, which is what happens over years of operation. The compressor or the booster also is going to get fouled over years of operation. Now, what happens when you have all of them put together? So that's something that we are still currently studying. So I don't really have the results that I can present here based on the open domain configurations. So we do have some preliminary studies which I will talk about. When we start imposing roughness or fouling on the booster stages, we see the pressure ratio degraded by about 6%, efficiency by about 3%, and so on. And that is just the booster alone. But what we see interestingly is that similar levels of roughness applied to a smaller blade like rotor 37, which is the booster blade, as compared to a larger blade like rotor 67, roughness has a greater effect on a smaller blade like rotor 37 as compared to rotor 60. So that's a rather interesting revelation that we observed, that a smaller blade seems to have greater effect of the same level of roughness or fouling than a larger blade operating all under similar conditions. So we also observe changes in the shock structure. This is the blade suction surface. This is where the shock occurs from the hub of the compressor to the tip, rough versus smooth versus rough. And this is for the larger blade, the rotor 67. So we see a stronger effect of roughness or fouling on a smaller blade like rotor 37 than what is seen in rotor 67. I'll skip this again. So what can be done about this? You know, when an engine operates over a period of time, it is going to accumulate dust and grime. And how do you address this? Well, it looks like the solution is very simple. It is just washing a compressor, and that's the term that is already used, and it is being done as well. Compressor wash that you can see here. This is the fan undergoing a compressor wash, and this is from the core of the engine. The wash, the effluent from the wash is collected and disposed. So compressor wash, this curve actually shows how it can be beneficial, a simple method like washing. This is the power output which it would if there is no wash done, this the green curve. And every time there is a washing done, it leads to a substantial peak in the performance soon after wash. And then again, it's going to, of course, progressively degrade. But one can recover this much of power loss or a thrust loss or efficiency loss, which would otherwise happen in the absence of compressor wash. Now, the question is, how do you decide at what point you need to wash a compressor? Of course, there are so many hours of operation one should wash and so on. But isn't there a better way to predict the buildup of grime or fouling on the compressor blades so that one can schedule these maintenance or washing in a more effective way so that the engine downtime is minimized? So that's something that one can perhaps do by a better understanding of buildup of dust or grime on the compressor blades. And that is something that will need a little bit more in-depth understanding of what causes or what leads to a progressive buildup of fouling on the compressor blades. So I would like to summarize here. I've exceeded my allotted time by a few minutes, but I would still like to summarize by a few points. Fouling of compressor or fan blade is inevitable because, and more importantly, it leads to a substantial degradation in the performance and output. 2 to 3% output loss is significant even under design conditions, and adverse conditions, it is an order of magnitude higher. So that is a substantial loss in performance. So how do we address that? So there are studies which show what the effects are on the compressor performance, but what could perhaps be done in terms of addressing these effects is something that needs to be studied more carefully, and researchers like myself and many others are use this as an opportunity for us to try and understand the buildup of fouling on compressor or fan blades. One could look at this design optimization or active or passive flow management. Better modeling capabilities, for sure. We have seen how roughness modeling by commercial solvers are, and they are significantly off from test data. And one could also look at the combined effects of these so that we have a better understanding of the buildup of fouling, which is inevitable. But is there a better way to predict these, which will help us schedule compressor wash at regular intervals to minimize the fouling effects? And improved component performance, especially that of a compressor, would indeed lead to better performance of the engine as a whole, and therefore lower fuel burn. And that's the key here, that one could come up with a methodology which will help us improve the fuel burn of existing engines. By the time we get to 2015 net zero and so on, we will still have thousands of engines in service, and one would have to live with the fact that these are all going to be exposed to the environment and will have adverse effects of dust and grime buildup. How do we address them till such time? At least we could minimize fuel burn by improving our understanding of how fouling of a compressor happens and how we can address this through a simple method like maybe compressor wash, and keep it as keep the products that are used in compressor wash as well something that are products being sustainable in themselves. So I would like to wind up my talk here, and I'm happy to take questions either now or during tea break in the interest of time. If that is, if you're closing for tea break now, we could also take questions at that time. I leave it to Dr. Prashant to decide. Okay, in case they have questions, I'm happy to address.
So, what are the implications of advanced propulsion systems such as boundary layer injection or compared to regular gas turbine engines?
Yeah, BLI propulsion. In fact, I think Frank and even Theo's talk had that. BLI is one way of exploring a different configuration than the traditional tube and wing configuration that we've all seen and we use. So BLI helps us look at a different blended wing aircraft configuration using smaller engines, smaller propulsors, and are more amenable to maybe electric or turbo electric configurations. So that's a configuration that seems promising, and but then it's a completely different engine architecture, aircraft architecture. But there have been studies like NASA's N3X and so on, very promising, but still concepts as we speak here. Thank you.
Good afternoon, sir. Sir, as you said, the very first impact of the compressor that the disbalance of air intake while the aircraft is flowing, due to which the fouling occurs. So, can we redesign the shape of the aircraft engine to avoid fouling and further process?
Yeah, so there are two aspects here. Fouling is not necessarily caused by distortion of the. Distortion is a very temporary effect which will have an impact on the stability of the compressor. Fouling is even during normal operation due to dust accumulation. Now, the BLI propulsion that the previous student had questions about is a system where the engine is submerged in the boundary layer. So one will have to design an engine or the fan that is always partially submerged in the boundary layer. It's always like it's operating in distorted flow all the time. So they have to design what are known as distortion tolerant fans. So there are works which you will find in literature which talk about designing fans which already take care of this distorted inflow. So there are ways in which one could address that, but those are meant for very specific applications like boundary layer injection engine and so on. So there are ways in which one can design a fan which will already account for the presence of a distorted boundary layer.
Thank you, sir. Good afternoon, sir. Sir, my question is, how do you see the hybrid electric propulsion evolving in next decade? Like, it will be a targeting transformation or it will be for a longer term?
I'm not sure if I have the complete answer to that, but hybrid electric or turbo electric, if I may, is like I would say, near-term possibility of going towards full electric aviation eventually, because you will still need enough power during takeoff. That's when you need the max power, and that's when you are likely to need a turbo engine to give you that additional thrust just during takeoff. And then once you reach your cruise altitude, your thrust requirements go down and you could still manage with just electric at that time. So you might want to explore till the time we have batteries which are sufficiently energy dense. I think hybrid electric, turbo electric systems would possibly be the medium-term solution to going towards electrification. Yeah.
Thank you, sir.
All right, thank you very much. Okay, sure.
Good afternoon, sir. Sir, my question to you is, what do you think about nuclear pulse propulsion?
Oh, wow. Nuclear pulse propulsion, I don't know if I have the right expertise to address that question. Some of my colleagues do work on that. In terms of aviation, I'm not sure that's something that is being considered, but for deep space exploration, I'm sure ISRO is already working on plasma and nuclear propulsion, but I myself have no expertise in nuclear propulsion, so I don't think I will be the right person to address that. But not for aviation, I don't think we have explored that yet, or we will. But for deep space, it's already been explored, and there are a lot of works even in ISRO happening on nuclear propulsion. Maybe you should talk to Dr. Ashok to get some more insight into that.
Sir, one more question. Do you think we can use a stellarator in a nuclear pulse propulsion?
Again, it's related to nuclear. I would not be in the right position to address. I may say something which may not be correct, so I don't want to venture into that. Sorry.
Thank you, sir.
All right. Thank you very much.
Thank you, sir, for sharing all the knowledge you have gathered for several years with us. Now, I would like to call upon the stage our conference chair, Dr. Prashant GK, to give the token of love and respect to Professor A.M. Pradeep. Following the keynotes, now we will proceed towards the technical tracks. So here are the tracks that will be going to happen with the venues and the theme. So all the people in the audience who are presenting the paper, please see the venue. Where is the technical track going on right now? I mean, it will begin after this.
Dr. Sami Gilius, P engineer, a distinguished leader in aerospace engineering and turbo machinery. With over 3 decades at Pratt & Whitney, Canada, Dr. Sami has played a pivotal role in advancing turbine aerodynamics, leading large teams, driving innovation, and shaping global engineering strategies. His contributions extend to academia as an adjunct professor at Concordia University, inspiring future engineers through his expertise in gas turbine design. An accomplished researcher and inventor, Dr. Sami holds numerous patents and has co-authored influential publications. His dedication to engineering excellence is further reflected in his active participation on industry boards, committees, and advisory panels, both nationally and internationally. Now, we request Dr. Sami to deliver the keynote lecture on the path to sustainability, opportunities for the next generation of gas turbine engineers and researchers.
Well, thank you. Thank you very much for that wonderful, wonderful introduction. First of all, I'd like to say I'm sorry that I couldn't be there with you in person to deliver this material, but thank you for allowing me to present it remotely. As it was mentioned, I've been both on the industry side and over the second half of my career, very much on the academic side, trying to help influence in my own way the path of future gas turbine engineers to get them ready for what awaits them when they enter into the workforce. So what you're going to notice in my talk this afternoon is I won't go too deeply into the technologies that we are working on at Pratt Canada as far as sustainability, but rather I want to try to shed some light into the kind of skills that our future gas turbine engineers are going to need in order to propel us into the future. So I'd like to share with you just a few words of who is Pratt & Whitney Canada. I'll talk to you about, technology pathways towards net zero by 2050, and more specifically, some of the initiatives that we're working on to try to address that. Some of the enablers to that path, both public and private investment, partnership and collaboration, a few words on AI as well. And then try to close on what this all means for the next generation of gas turbine engineers and researchers in the future. So Pratt & Whitney Canada is part of something quite big. We're a part of 3 major business units that all fall under Raytheon, both Collins Aerospace, Pratt & Whitney, under which Pratt & Whitney Canada resides, and Raytheon. The 3 combined businesses account for $74.3 billion in adjusted 2023 sales and are about 182,000 employees strong. Pratt & Whitney Canada specifically, we have a little over 15,000 employees worldwide. We deal with over 16,000 operators on 744 airlines. Currently, as of last year, over 42,000 aircraft in service, 68,000 engines in service in 195 different countries and territories with 1 billion plus operating hours. So we like to, at Pratt Canada, we like to brag about this, but it is true that every second somewhere on the planet, a PWC-powered aircraft is either landing or taking off. And all of these flights matter, whether they're powering humanitarian missions, emergency medical services, search and rescue missions, reuniting families, driving commerce, even, more recently, helping to fight forest fires in LA and California. So we have one of the largest and most capable networks in the industry, more than 50 owned and designated facilities, one customer first center in Montreal that's open 24 hours a day, 7 days a week, 12 flight training schools through Flight Safety International, over 100 field support representatives, over 100 mobile repair teams, over 1,000 rental engines, 40,000 plus new and used parts available for purchase, 10 owned and designated parts distribution centers that can typically get a spare part to a customer in 12 hours or less. So that gives you an idea of who Pratt & Whitney Canada is and what we do. Now, we've all seen this chart or variations of this chart. And when I look at this, it's clear that when we look at engine and aircraft technology, couple that with sustainable aviation fuels, between those two categories, when we talk about enablers of getting us down to net zero by 2050, they may well be responsible for 80 to 90% of that path. So I'd like to share with you a little bit of what we're doing at PwC around those two themes in particular. So we've been making significant investments and incorporating many enhancements in fuel efficiency. No matter what ends up happening on all of the other paths, every bit of additional fuel efficiency we can incorporate into our existing fleet of engines just brings us that much closer, or leaves a little bit less there for the other technologies to have to deal with as far as getting us to net zero. We're also working hard to demonstrate full sustainable aviation fuel capability in our engines. And since 2021, we announced in partnership with our government the intent to invest $162 million to demonstrate hybrid electric propulsion. Again, goes along the line of improving overall fuel efficiency at the power plant level. And recently, we launched initiatives to demonstrate hydrogen combustion technology in one of our most modern turboprop engines. So I'll say a few words about each of these in the next slides. When we look at the geared turbofan engine, this was launched back in 2016. The idea here was to put a gear between the turbine and the fan, essentially turning a turbofan engine to a turboprop engine, because we're able to run the fan turbine at a higher speed and the fan itself at a lower speed. We're able to run each of those components at a more optimum efficiency, and as such deliver better fuel consumption and lower emissions as a result. So it's not a new concept, but our differentiation has given the ability to employ this architecture at over 30,000 horsepower equivalent through the small fan drive gear system with very high efficiency. So we launched and are executing the development and certification of the geared turbofan Advantage, and that Advantage enables us to extend this even further, delivering more thrust, additional 4% at sea level and up to 8% at altitude, while delivering an additional 1% better fuel burn and increased durability. The engine, by the way, is ready to operate with 100% SAF. And with the geared turbofan Advantage, no other commercial engine can match this efficiency, emissions, and noise reduction footprint. So, what you see there is what's already been certified. Numbers like 17% less fuel burn and CO2 emissions is quite substantial when we look at a brand new family of turbofan engines.
Excuse me, sir.
On the Pratt & Whitney Canada side, again, here we took our well-established PW100 family of engines and were able to retrofit some state-of-the-art design solutions, such as advanced LP compressors, advanced power turbines, and we're able to deliver for an engine that was already quite fuel efficient, an additional 3% fuel efficiency improvement. And all of this happens while lowering maintenance cost and increasing time on wing.
Excuse me, sir. Just to confirm, sorry to interrupt you in between. Are you changing the slides?
Oh dear.
Could you please verify if the slides are changing?
I am so sorry about that. I won't rewind. I will start off where I left off. I'm so sorry. So we have multiple demonstrations of engines being able to run with SAF, from the geared turbofan engine that I mentioned already to more recent demonstrations in test cells as well as in flight. We've got V2500 demonstrations in test cell with 100% SAF last year. The PW127 XT engine I mentioned before also had flight testing with 100% SAF, demonstrating readiness for the Dornier 328 Eco aircraft. And earlier on, PT6C engines in an AW179 helicopter completed a 75-minute flight with 100% SAF. I mentioned earlier about hybrid electric propulsion. In 2021, we announced an investment of $163 million with the support of our federal and provincial governments, with the aim of demonstrating hybrid electric propulsion in flight. So PwC is working with de Havilland Aircraft of Canada Limited to integrate this hybrid electric technology into a de Havilland Canada-8-100 flight demonstrator. So this demonstrator will include an advanced electric motor and controller from Collins Aerospace, which is also a Raytheon Technologies business, as I mentioned earlier. The idea here is to demonstrate a 30% fuel burn and emissions reduction when compared to conventional turboprop applications. So as you can see in the chart, there are many aspects to achieving this 30% fuel burn demonstration. The idea being using the thermal engine and electric motor during the parts of the flight when they are most useful. But what's proving to be the big challenge is how to integrate all of these into an overall demonstrator. And we're looking forward to being able to demonstrate this in flight sometime very soon. When we talk about sustainable aviation in Canada, the aerospace industry is one of the most innovative and export-driven sectors in Canada, contributing close to $27 billion and more than 210,000 jobs across the Canadian economy. So in partnership with the aerospace industry and in line with Canada's Aviation Climate Action Plan, in June 2023, the federal government announced that it was investing $350 million to support the country's new initiatives for sustainable aviation technologies. It's so-called INSAT. The intent of this investment, of course, is to accelerate the green industrial transformation of all of the aerospace industry and what Canadian aerospace industry players can do to enable that. And so I'm sorry, just bear with me. And so in the fall of 2024, as part of this INSAT initiative, PwC has demonstrated hydrogen combustion technology on a PW127XT as part of this INSAT. It's in collaboration with Next Hydrogen Solutions, Inc. The collaborative project with INSAT enables us to develop key technologies for future hydrogen-powered aircraft and complements our wider efforts to advance aviation sustainability through a range of pathways, including continued improvement in engine efficiency, as I mentioned earlier, hybrid electric propulsion, as I mentioned, and compatibility with sustainable aviation fuels. So funding for the first phase of the project included fuel nozzle and combustion rig testing using hydrogen fuel, while future phases are going to target full engine ground testing. So as part of the second INSAT-supported project, Turbine Engine Advanced Materials for Efficiency, Pratt & Whitney Canada will work with derivation research laboratories to explore advanced materials for hot section components of gas turbine engines. As we all know, peak cycle temperatures are the enablers for power density. However, we need to be able to do that without increasing turbine cooling flow consumption. And hence, we see this as a path towards improving thermal efficiency as well as reducing fuel consumption and emissions in the future. So this is another initiative that we've launched recently. Among the INSAT-enabled projects I mentioned before, we're working to demonstrate combustion technology on the 127XT regional turboprop engine. The project has been named Hydrogen Advanced Design Engine Study, or HIADIS, and it's in collaboration with Next Hydrogen Solutions, Inc. And the funding for this project, as I mentioned earlier, includes fuel nozzle combustion rig testing using hydrogen fuel. And here the idea is to get all of the other components ready for this. And many opportunities here of this project, including exhaust waste heat recovery, electric engine actuation, and the like, are all going to be explored as part of the same project. Now, I'd like to say just a couple of words about AI. We all talk a great deal about AI, and it's evident that all of the avenues towards achieving net zero by 2050 will, in one way or another, be enabled or facilitated by AI. So we see AI today as the next evolution of engineering capability. If we take the 1800s, for example, as state of the art of more modern engineering, we look at the first 150 years or so, and we're pretty analog in terms of engineering tools. In the late 1960s, computers start giving engineers powerful tools for design, including early FEA, CAD, CFD, and then multi-physics analysis. Around 2010, we see at Pratt starting experimenting with using machine learning methods to turbocharge our ability to do multi-physics modeling and design optimization. And since then, we've started to apply AI technologies to more applications in engineering, including classifying oil samples and even helping with quality control. So I want to talk for a few minutes about what AI means and how it might change how we work, and more specifically, how the future generation of gas turbine engineers are going to learn to work. Although AI technology is advancing quickly in many applications like in engineering, it's still very much in its infancy today. However, we see how the AI transition is taking place. Many of these transitions will be a double-edged sword, creating new opportunities and new challenges. For example, it's likely engineering will continue to become more multidisciplinary and systems-oriented, and it's going to give us a chance to cross-train and learn new disciplines. There are even roles for multidisciplinary optimization engineers to coordinate integrated modeling for a component or system. So with a domain, our analysis tools will become much faster and more powerful. And this will bring us from tighter integration of traditional solvers and machine learning systems. It gives the discipline experts the opportunity to bring more complex insights, usually saved for detailed design, up much earlier in the engine design programs when there's a chance to influence the overall engine architecture in a much more profound way. And as data management initiatives become more mature and data generation accelerates, information is going to become more accessible. But if we manage this all carefully, it could lead to overload and paralysis. So it's going to require careful attention to topics like uncertainty modeling and propagation, so that we're not generating new analysis because of the low uncertainty of understanding of other analyses. So what does this all mean for the next generation? Whatever the future is going to look like, future gas turbine engineers will have to continue in the relentless pursuit of efficiency. Not only because today's engines are going to be around for a long time, but regardless of what future technology we deploy, it will have to rest on the most efficient base that we can provide. And of course, this will always require a very solid understanding of thermodynamics. This is never going to go away. The future gas turbine engineers will have to be able to think at both component level and system level, because clearly both of these areas are key to achieving net zero by 2050. And this includes a deep understanding of both the engine and the aircraft system. The future gas turbine engineers are going to have to understand the implications of sustainable aviation fuels and hydrogen, both at a macro and micro level. And as new tools such as AI emerge, future gas turbine engineers are going to need to be prepared to embrace these tools and leverage them for all that they're worth. At Pratt Canada, we believe very much in innovation through collaboration. And here we work with governments to better the future of all aerospace industry stakeholders in Canada. So Pratt & Whitney Canada has worked with the Canadian government towards investing $350 million to support this initiative I talked to you about earlier called NSAT. We work collaboratively to generate new next generation sustainable aviation fuels in Quebec and Canada. And we're an active member of our community, bringing aerospace at the forefront of social and economic success in the future. When I talk about academic collaborations in Canada, we have over 15 research projects with universities per year. We engage with more than 450 student internships per year, invest over $10 million a year in academic collaboration across Canada. We're active in over 20 university research agreements, and we support 6 research chairs across Canada. So you see there a couple of examples, but this is by no means the complete list of some of the research teams that were involved in this academic collaboration effort within Canada. I talked earlier about future gastrobiome engineers needing to be able to be both experts in specific areas, but also have a good understanding of the overall engine system and aircraft systems. And so in 2022, we launched a new program at Pratt & Whitney Canada for the hiring of new engineers. Our new engineers now will go through a rotation within engineering that spans over 3 years and consists of 3 assignments, 1 year each. The residency, a lapse of 1 year, was selected to give enough time to learn the basics of the work and be able to complete meaningful tasks. And the total duration of the program was defined to give a variety of experience while maintaining a reasonable duration. Once the employees complete this 3-year rotation, they get assigned to a department in a function, which is a function of the company needs and the employee skills and interest. And we feel that, you know, this is going to contribute towards employees being able to have a steeper learning curve as far as being able to learn all aspects of the business and have a better understanding of the overall ecosystem within which we operate. So to summarize, it's clear we're going to need to use all of the tools at our disposal to address climate change. Whatever the future looks like, we'll have to continue the relentless pursuit of efficiency, not only because today's engines are going to be around for a long time, as I mentioned earlier, but because regardless of what future technology we deploy, it will rest on the most efficient base that we can provide. We're working to ensure that our engines are compatible with the greenest versions of SAF as they emerge over time, and will support industry efforts to release 100% SAF fuels as the most crucial element of near-term climate aviation decarbonization. We see clear benefits of hybrid electric moving forward in the next decade. We know this because we're using digital modeling and sophisticated simulations to design these future configurations. We're beyond excited to demonstrate the potential of hybrid electric propulsion technology in demonstrator programs, which we have completed many of those on the ground so far, and are collaborating with Collins Aerospace on developing technologies and products based on partial or full electrified propulsion. The time is also right to look again at the opportunity into that hydrogen fuels present. We're so excited to work unique concepts such as high site, but the propulsion system is, of course, only part of the challenge. Viable service entry will also depend on incorporating the engine into an aircraft designed to carry hydrogen fuel and having a hydrogen delivery infrastructure available at airports. We also need to continue to consider the potential effects of hydrogen combustion on contrail formation, which could have an associated climate effect. So fortunately, we're already seeing steps being taken to address these. And when it comes to the opportunities that lie ahead for gas turbine engineers of the future, whether they're still completing their studies today or recently entered the workforce, it's fair to say that they'll have no lack of exciting and challenging problems to solve as they get us to net zero by 2050. So thank you very much for listening to my talk.
Hello. Good evening, sir. My question is, how did you plan to, did you or did you not foresee the issue with powder metals in your engines, which were the cause of grounding of many Indigo aircrafts? And how do you plan to resolve it and ensure it does not happen again in the future?
That's a very tough question. I won't be able to take that question here, as it's something that pertains to our parent company, Pratt & Whitney. So I'd rather be safe here and not make any comments in public about that. I'm sorry.
Sure, thank you.
Yes, please.
Thank you, sir, for your very insightful words on the topic.
One question.
One.
Sorry, sir. Yeah. Sir.
Good evening, Dr. Gargi. Good news. So I have a question regarding that hybrid propulsion system which you are working on it, right? That is thermal and electrical things. So how are you planning to, do the battery management for the electrical propulsion?
So we're working on developing all of these systems together. I can't share at this point too much detail in terms of the battery management system, except that the project is looking at ultimately being able to fly on the aircraft you saw the picture of earlier. And so we're dealing with all of these issues as we speak. But again, it's everything is still a work in progress, so I can't really share with you too much more detail at this stage.
And are you also considering the DEP, that is a distributed electrical propulsion, when you go for that hybrid, right? Because that DEP is one of the, energy saving method, right? To instead of having that one side propellant, you go for example, if you are going for hybrid, it's a good idea to have that electrical separated with the DEP concept, having that thermal separate, separate instead of having propeller also on the same line, right? So,
yes,
are you considering that proposal also, or are you considering whatever the concept you are shown in the picture now?
No, in fact, the concept that I showed there was just one of many concepts that we're exploring currently. The concept I showed here was really just pure hybrid electric, being able to power the same prop, be it by electrical or by the thermal motor. But we do have multiple other projects ongoing when we talk about distributed propulsion, and many different other concepts as far as being able to use electricity and a thermal motor in different ways, and even potentially the thermal motor just being involved with electricity generation purely. So yes, the answer to your question is yes, we are looking at other avenues of distributed propulsion as well.
Yes, another point, right, regarding that hydrogen propulsion, right? What exactly your safety measures you are taking to store the hydrogen fuel? It's one of the key things, like it can explode or whatever, right? The safety is the key here. Like, how are you working on the safety precautions for the hydrogen propulsion system?
Yes, absolutely. I think we're still very much in the early phases right now of exploring this avenue, looking more at just the combustion side of it. But there's a lot more work ahead of us before we can overcome all of the other safety issues, for sure.
Last question: how far you are proceeding SAF in your PW engines now? Like, what is the percentage of implementation you are considering in the SAF into your propulsion system?
We've already had multiple demonstrations that show that once there's enough availability of SAF fuel supply, our engines are pretty much ready tomorrow to be able to switch over. So we've already completed quite a few demonstrations, and I'm sure there's more to come. So I think on the engine side, we're more ready, let's say, than on the supply side.
Thanks, Dr. Giris.
Thank you, sir, for your very detailed keynote session. It was an honor to have you here.
Thank you. Thank you very much for having me. I wish you all a good rest of the day.
Moving forward, Dr. V. Ashok, former Associate Director of Vikram Sarabhai Space Center, VSSC, has over 3 decades of experience in aerodynamics, CFD code development, and chemically reacting flows. After earning his BTech in Mechanical Engineering from College of Engineering, Thiruvananthapuram, and an MTech in Aerospace Engineering from IIT Kanpur, he joined VSSC in 1989. He played a key role in developing PARAS-3D, a parallelized Cartesian mass-based CFD solver widely used in Indian Aerospace Lab. He also contributed to major ISRO missions, including LVM-3 Chandrayaan, Usable Launch Vehicle, Scramjet Technology Demonstrators, PSLV Aditya L1, and the upcoming Gaganyaan mission. He also represented ISRO in the Interagency Space Debris Coordinate Committee, driving advancement in spaceflight and aerodynamics. Now we request Dr. V. Ashok on the stage for delivering his keynote on challenging flow problems in launch vehicle and re-entry mission.
So thank you for the nice introduction, and let me first of all thank the organizers for giving me the opportunity to share the experiences I had with VSSC with this audience. I know the students here, whomsoever I met, they are all very, very charged up and very anxious and very keen to know many of the aspects. So I will just give a glimpse of what is really happening in VSSC. Because there is a lot of mind to cover, so I'll go a little fast, so you will get an overall idea, and then whichever topics you are interested, we can further talk in the evening dinner time or so. So, so I'm going to cover mainly on the challenging problems in launch vehicle and re-entry missions. Well, the genesis of the Indian space program started in this St. Mary Magdalene Church in 1963, Tumba. And then later on it became a museum. Dr. Kalam always says how the priest there told that this church is now going to become a center of learning in science, and how this church became our center first. So that was the story is often quoted by Kalam. And Tumba is a fishing village in Trivandrum, Thiruvananthapuram now it's called, and was selected to establish the first rocket launching station because the magnetic equator passes through this place, and so we can do some special experiments called the equatorial electrojets. So that is why it has an interest in space physics. And so this is the ignition of minds, APJ Kalam discussing with Dr. Sarabhai at Tumba. And you know, that is Indian Space Organization was formed in 1969 under the Department of Atomic Energy. Both were together. In fact, Vikram Sarabhai was holding both the Department of Atomic Energy as well as the Vikram Sarabhai Space Center, and Sarabhai was this chairman. Now, a little bit about Vikram Sarabhai. So you know that he had told that we should be second to none in the application of advanced technology of real problems of man and society, and he studied in Oxford. And this is the Rabindranath Tagore's recommendation to Vikram Sarabhai to put me in Oxford. He said, "With great pleasure that I recommend the application of admission to Mr. Vikram Sarabhai to the authorities at Cambridge University." Sorry, it's Cambridge University, and he is a young man with keen interest in science and etc. And so that's how it is. And these are all the pictures, and this is on the Little Prince story. Well, now I'm going to talk about fluid mechanics and what is the contribution. So right from, you can see here, from Archimedes to Newton, where you know Newton's law is there, where you use the Newtonian fluid. All the equations we solve is considered Newtonian. If it is non-Newtonian, it is more non-linear. Then you have the Bernoulli, the Euler, and we solve the couple of partial differential equations. These are all the equations which is all the famous Navier-Stokes equation. And if you have a closed form solution for this equation, you don't need to have any of this parallel computing and things like that. So all of these, we start doing solving this equation, and these are some of the great people in fluid mechanics, Reynolds, and you know the Reynolds number. You know, Ludwig Prandtl is the father of modern aerodynamics. The great man, he very narrowly missed the Nobel Prize, and of course Taylor is another person. And as far as India is concerned, it is Satish Dhawan, who is can be called the father of experimental aerodynamics in India. Because he first established the tunnel in the Indian Institute of Science, Bangalore. He was holding both the Indian Institute of Science as well as Sarabhai. In fact, when Mrs. Gandhi called him, he was taking a class in Calcutta. And then he told that, yes, I'm taking class now. I'll call you back later after the class. And that's our stature here. So he was holding both of them. And these are his pioneering contributions: direct measurement of skin friction, shockwave boundary interaction, and development of turbulent transition model. Dhawan Narasimha model is the very famous model, 1958. And these are some of these pictures. And what is Lippmann told about? Lippmann-Roscoe is one of the very famous book in gas dynamics. And what he told, Professor Dhawan and I have been colleagues and friends for a very long time. By now, he has caught up with me in everything except age. And this little study is offered as a tribute to Dr. Dhawan as a small token for a great scientist. You know, he was from Srinagar and he did his engineering in Lahore Engineering College. Well, so let us come to the space system technology. Is multidisciplinary, as you know, and all the speakers have told that it is not just one discipline. We have all the things: mission design, propulsion, aerodynamics, thermal design, structure, navigation, guidance, control, avionics. So all the things are there to make this launch vehicle. I happen to be in the aerodynamics and propulsion and a little bit on the mission design because I happen to head the aeronautics entity there. Well, this is one slide which says what essentially is a launch vehicle and what are the challenges involved. Like from the liftoff to placing the injection of satellite in the orbit. What are the various problems that is involved here? At the liftoff, we have lift-off jet interactions with tower, wind dispersions, pre-launch operations and checkout involves a lot of avionics. Propulsion, structure, control, aero interaction during the atmospheric phase. As you know, we try to cover the atmosphere as early as possible. And then you have also the trajectories there. And you know, this is you design a trajectory in such a way that the energy is optimal. That is, there are three losses that are to be taken into account. One is the gravity loss, the drag loss, and the steering loss. To steer the vehicle, you have a loss. So the problem is posed mathematically to say what is the trajectory y f of x, which gives these three losses together, minimize these losses so that I can put the payload, maximize the payload. So it is essentially solving a differential equation, and it's again uses variational calculus. But as you go through the atmosphere, you have shock oscillations, unsteady lows, you have this base heating, thermostructural interactions, combustion instabilities, and then when you cross the atmosphere, you have inertial navigation, guidance control, auto loop, autopilot, nonlinear sensor aerodynamics, and thrust of transients, and various separation systems are there. And when you inject it in the orbit, you know, we always do Monte Carlo simulations because nothing in engineering is perfect. There are always dispersions. There is dispersion in thrust, there is dispersions in the navigation system, the dispersions in control system, dispersions in aerodynamics. So all these dispersions put together, how a system behaves is done using Monte Carlo techniques. And space debris mitigation is another very important to see that now before we launch a satellite, we see whether there is a probability of hitting the debris or not. That's why some of our launches gets postponed by something like 1 minute or 2 minutes. Even the recent SpaceX where we did docking, we postponed it by 1.5 minutes. Well, this is some of the applications because there is nothing like case studies. This is one study which we have done in the GSLV in 18th March 2001. You can see there is a ball of fire that is there between the tower and this vehicle. And what is the cause of this we wanted to see? And we can see here with the simulations, we could see that there is these jets that are impinging here is going back. But when we put the fountain jet preventer is what it's called is left put, and then you can avoid that. And for this, there is a movie there. If you can put that, you can play it, and then you can be shown both of this together. Otherwise, we'll move to the okay, fine. So that is the problem. And the next one is the effect of jet on the stability of launch vehicles. We can see here. Now this all the wind tunnel tests are done without the jets because we cannot simulate the jets. It's very, very costly to simulate jets. There are no jet-on facilities in India. We have to go to Russia to do this test. But if you with the jets on, you can see here there is nothing that is happening in the forebody, but in the base there are some differences, and it actually moves the stability. It reduces the stability. The center of pressure moves forward because of the lower load that is coming here. So that is the aspect of which has to be taken care. Well, these are the various problems that are there in launch vehicle. On the left-hand side, we have all the aerodynamic problems. That is, as you go through the atmosphere, the atmospheric pressure drops, and there are some compartments which has to be vented out. If you don't vent the compartment, then you have 1 bar atmospheric pressure, which is very, very large. As you know that the structural loads has to be minimized and the structural weight has to be as low as possible. The factor of safety is very less, 1.2 or so. So unlike the civil structures. So what is needed is to have this appropriate venting procedure so that the differential pressure across this is minimized. Then you have the shock oscillations. I feel that you should click this, and then we can see the movie of that. That is with a straight nose cone, we will see how the shock will oscillate. You just click on that. No, on that side. Yes, left. First you go to the left one. Yeah. Yes, please. Let me. How the shock oscillates here. See, on this side you have flow separation and the very violent shock oscillations are there. Now what has happened is this is very high unsteady loads and it gets transmitted to the satellites. So we need to minimize this loads on the external aerodynamic loads on this, the unsteady loads. This is on the start ones. Yeah, let's stop that. Come out. And go back there, and then you can click this. So this, then if you do an ogive, that is, if you have instead of this standard a straight nose cone, if you have an ogive, that is a very smoothly gradient profile. You can see the flow separation is avoided. You don't see a flow separation there. So the much lesser acoustic loads, which is very good for the satellite. Can go back. Yeah, so it is something like a fluid dynamic zoo, you can say. All types of flow is seen on the launch vehicle. You have an laminar attached flow to start with, then becomes turbulent, then you have a shock waves, then expansion fans in the corners, vortices are there, shock wave, vortex interactions, separate flow, base flow, jet interactions, and reverse flow, and shear lace, etc. So it is something like all types of flow is there, but there are still gap areas. What are the areas? Many people are asking me, what are the areas which you need to work? These are some of the gap areas. Computational aeroacoustics, how do you measure the noise on this? The aeroacoustics is still a very gray area because you need to really follow the turbulence to get this understanding of this. And the structural response to aeroacoustic excitation, suppose you have a random acoustic noise that is coming, how does the structure respond to that? Vibroacoustics is a very gray area, and this again experimental estimation of multi-jet interaction. This is what I told, no facility exists in India. Well, this is the concept of base heating. As we know, as the launch vehicle goes, climbs the atmosphere, this is at Mach number 0.8, that is, it is just nearing transonic, where the atmospheric pressure is not that low, so the jet doesn't expand that much. And as it climbs the atmosphere, the jet keeps on expanding. At Mach 2, it is more expanded. At 2.5, it is much more expanded. At 3.5, you can see a very strong expansion is there. And this shock and this shock will interact, and this forms a very strong shock. And the flow that is coming here is not able to penetrate the shock. So what really happens is you have a shear layer and there's a reverse flow which gives a base heating. Now what we need to do is we have to design the systems, the thermal protection system, so that you have the base heating is avoided. So we have to quantify this base heating first and then do appropriate experiments to design the thermal protection system. So that's what is done here with thermal boots. Well, this is on the how we change from the LVM3D1 to the LVM3X to LVM3D1. This is the first experimental flight of Mach 3, which had a straight nose cone, and all these are straight cones. We changed it to this because this was really beneficial for us. As I showed you here, this has a far lower acoustics. Even on this region also, we have the lesser acoustics. What really happens is we have the vortex that is coming through from this strap-on to core attachments, which will interact with the shock waves. You have a shock vortex interactions, which gives again very high levels of acoustics. And so that's what you can see here. The levels of acoustics is given here in X, and how much this X plus on this side, X plus 14 has become X here. You can see here there's so much of difference in the acoustic levels and decibels, which has really benefited this particular aerodynamic design. And you can just press that, see this one here on the, can you press here? Yeah, just press it. So you can see here, this is on the straight nose cone, how much the large scale separated flow is there. The other one is much contained. Yeah, you can. So we'll go to the next one. Well, these are some of the challenging problems which I have just listed here. And this is what we have already done. That is a RLV TD, that's a reusable launch vehicle technology demonstrator. The scramjet we have done, Mark 3 and landing experience we have done, Chandrayaan 3. And this is what we are now going to do. The test vehicle, the Gaganyaan, the RLV orbiter, which is going to come from the orbit, and the airframe will get scramjet. And these are the facilities which we are building. Now we have a capability to do experiments from Mach number 0.2 to 12. This is the hypersonic test facility from Mach number 6 to 12. And this is, we have going to have a 2 petaflop supercomputer, and 1.2 meter trisonic tunnel is already operational. So all the way from Mach number 0.2 to 12, we'll be able to do experiments. And these are some of the challenging problems. Dynamic stability of 2 modules, challenging problems in one web mission, which I will going to highlight. Parachute inflation dynamics with fluid structure interaction. What happens when the parachute inflates? That particular problem is another very complex one, and inflatable aerodynamic decelerators. Well, this is some of the problems which we did for the Chandrayaan 3. And in the Chandrayaan 2, what happened was we had 2 engines, and these 2 engines again, they start interacting, and when they hit, they just land on the moon, the dust gets thrown up. So we avoided this by putting a single nozzle there, and then this problem was not there for the Chandrayaan 3. But then, however, still there will be base heating because of in the upper atmosphere, when it is before landing, there are interactions between these jets, and that was quantified and seen how much is the base heating that is happening. Well, this is another very interesting problem on the LVM-3 OneWeb mission, in which we have to launch the 36 satellites, OneWeb, in one go, and we had 2 such missions. It was a very, good commercial mission because it was on something like 1,000 crores or so. But then we had to have a design mission for this, and very novel method of doing the mission design was done. This is the orbit specifications, and the mass of the satellite was 5,796 kg. And here we will see the sequence. You can just click here how the sequence is done. So we have this first to separate the satellites, and then what happens is you turn the vehicle. Now you have the cryogenic fluid inside, and with this cryogenic fluid you are going to turn the vehicle, and then we have a host of problems related to this turning of this vehicle in zero gravity, when there is this cryogenic fluid also gets evaporated. So it's a typical case of a 2-phase flow in a tank in which there is an evaporation taking place. And then because we need to add because the condition they are told is the minimum separation distance between the satellites should be at least 200 meters. So we need to add some velocity to this, and for adding this velocity, we need to do like this, and then add the velocity by means of some, coming out, the venting the fluids out, and this is how then it has to again come back and again do the separations. So that was the very interesting problem here. Yeah, so this is the next step. Like this, we did the 36 satellites were separated, and this was the problem definition. The customer requirement of satellite operation by orienting this vehicle, and how to do it in LVM3, because we did not have the restart capability of the cryogenic engine. So without restart capability, how can we do this? So we can use excess liquid hydrogen and rocks carried by C-25, and what are the issues during the reorientation at zero gravity? We have the migration of the tank will be there, evaporation of LS2. So all those things were handled by this. We formulated this problem in the CFD, and then we had done the simulations to see whether any propellant is left over, is there or not. If there is no trapped propellant there, then this mission will be a failure. But finally, we could find through the simulations that it is possible to have this leftover propellant, and these are the different conditions of the leftover propellant and how the heat transfer takes place and how much is the leftover propellant there. So this is the simulation output which we have got, and this was finally successfully done. Well, then now we go on to the Gaganyaan summary, and this is to develop a human habitable space capsule to carry up to 3 members at 400 km and return safely to the predetermined destination. So we have the takeaways: human-rated launch vehicle should be here. There's not debris management, thermal protection, astronaut training, man-machine interface. All those things are involved in this. There are a host of technologies to be done. Of course, it is not just done by ISRO. It is DRDO is there. So many labs are involved in this, and several. It's almost the whole nation is a part of this particular venture. And this is some details of this, and this is the orbit and the inclination, and this is how we are doing. And we have a crew escape system, because at every 1 second you should be able to eject and see if there is any problem. It is done by the launch vehicle health monitoring systems. It detects whether there is a problem is there or not. It will eject, and the crew escape system along with the crew will come out as the escape system. And then, but after the first stage, this is ejected out, and we have the
the orbital module and the crew module, they travel together, and then the crew module alone goes, and then after some time it re-enters here, and then you have the re-entry where we have the high heating with the hypersonic, and then you have the drogue parachute and the main parachute, and comes down safely then near shore. And these are the various instances where, crew safety at any instant, redundancy, fault tolerance, we derate it. So what we do is we don't make any design changes. What we do is instead of 59 K 60 JSC, we'll make it to operate at 56 KSC, so that it's not an efficient way of doing it, but then it is more safe way of doing it. So safety given more importance. The factor of safety instead of 1.2 becomes 1.3. Robust fault detection system, stringent specifications for materials and processes. Well, these are the preparedness for Gaganyaan. We have the various, we have done a space recovery experiment in 2007. We had a CARE experiment, and we had also a reusable launch vehicle technology demonstration. We did a part about test in 2018, and then supersonic infrared aerodynamic systems, and we also have environment control systems and the special purpose motors, quick acting motors, that's called crew escape system motors. And we had really recently a test vehicle demonstration to see how we were able to eject this crew escape system and safely land it. And this is a special vehicle designed for this, because you making a full vehicle do this is very costly. So we have a test vehicle to do all these purposes. So we do the air breathing also with this test vehicle, the crew escape system, and also retro propulsion things all done with this test vehicle flights. Well, these are all the details of this, which will not get into details, but this was a flight in which we ejected at Mach number 1.1, and this crew escape system fell here, and the crew module along with the parachute fell here, and this is the spent stage booster that is coming here. So these are the various ranges that it is coming. This is at 6 kilometers, this is at 8.9 kilometers, and this is at 18.2 kilometers. Well, these are some of the studies which are done on both the wind tunnel as well as the computations. You can see here how the match is coming. So we do with several wind tunnels, several CFD codes, and see that they are all within the dispersion band. That's how the things work here. And we have done in the Glad-Cosmos tunnel in Russia. We have done in NAL. We have done in Incas, Romania, and also we have done the CFD also. And you can see the tunnel and the other things. They are all matches within very good, within 10%. So this is the confidence which is there in the aerodynamic coefficient that is generated. And this is another interesting problem. We can just click on that here. Can you just click it here? This is the yes. So this is how the separation along with the crew escape system, how it comes. So these are the simulations that are carried out to see that the separation is safe. Anyway, all these things went off well in the first slide. Well, this is again on the Gaganyaan mission profile. So end-to-end mission management, control flight through atmospheric maneuver using the reaction control systems. Aerothermodynamics is another important aspect, because the air that is coming when it re-enters, all the air will become plasma. And with the plasma, you have to analyze it, and you should also have a validation of low density TPS, thermal protection system, communication blackout management, because at that time when there is an electron cloud, you will not be able to communicate with the aircraft, and so you may have to store the data on board and later on transmit the data. So these are some of the problems of the re-entry hypersonics. And these are again some of the computations that are carried out. You have on the top side is the numerical Schiller, and on the bottom side you have the wind tunnel experiments, and these are all good matches there. And you can see here we have done communication blackout studies here. Electron number density variation is shown here. It's all full of electron cloud here. And you should be able to tell what is the cloud here, and what is the region in which you will not be able to transmit the signals from here. And on these corners will have very high heat flux, which you have to appropriately have the thermal protection systems. Well, these are the Indian perspective in sustained human space program. Technology development phase, 2 unmanned and 1 manned flights. Capability to launch humans and stay in space for 7 days is our goal. And this is the capability of human space. There's a long duration stay in space. And here we have Indian Space Station, deployable human habitat module, robotic missions, long duration stay, docking, EVA, and extravehicular activities and space structure assembly. And then on the still longer interplanetary manned mission, we are talking about mining of near asteroids, colonization of Moon and Mars. This is much ahead of 2040 and things like that. Well, then we'll come to some of the very interesting things on the re-entry technologies. This is on the reusable winged lander. And this we are now working, and we had already done a landing experiment, and this is on the air breathing hypersonic airframe integrated vehicle, wherein you go at you come to an altitude of something like 30 kilometers, and then you have Mach number 6 to Mach number 7, and this is the typical sketch of the airframe integrated scramjet engine. And this was one of the first successful things which we did, that we went to a pillbox in which the sustainer was put at mark number 6 at 20.1 kilometers. We started the experiment in 5 seconds of experiment. And this was the trajectory in which we have the various dynamic pressure conditions and various Mach number conditions. And what we could see, this is the 2 struts in which we had mounted a lot of pressure measurements in the center of this, and we had measurements of this, and we wanted to see whether we really got a supersonic combustion or not. And this was the sequence. The first, the cowl will be closed, it will be open when it reaches the correct Mach number dynamic pressure window. The cowl will be open, and then the combustion will happen. The fuel will be injected at the back of the strut, and then you have combustion with fuel regulation. And then in the blowdown mode we had, and this was the you can see here, this is non-reacting when there is no combustion is occurring in the behind the base. There is no hydrogen is injected, and you can see after various injection, the ahead of the strut there are no differences between the flow fields, which means that the combustion happens downstream of the strut without any upstream influence. So that's called the supersonic combustion. And you can see here, this is the flow with the non-reacting case, and this is with the reaction. You can see that the pressure rise just occurs only at the downstream of the strut, clearly demonstrating that the supersonic combustion has been achieved. And this is the one of the pressure measurement here at various instances, and these are the dots or the computations, and we can see clearly the play mode that is occurring at certain dimensions also has been properly captured. And with this, we are now trying to have an airframe integrated scramjet to achieve a positive plus minus drag, accelerating flight from Mach 6 to 7 for 250 seconds. And this is the angle of attack is 2 degrees. And then for this, we need to have the various design was done using the computations, and here the initial concept is the 77th configuration. Various design studies were done, varying the upper cross section area, wing aerofoil platform, wing incidence angle, wing location, etc. And all these effects were the filmability of the vehicle, wing location, everything was done. And then we have done with the hydrogen and later with the kerosene. And we have, so main thing is the configuration evolution, intake starting issues, supersonic combustion modeling, and tip to tail simulation. These are the various aspects of the things which are covered in this. And some of these interesting problems were that we found that this particular intake initially had a very strong shock that is coming and interacting with the boundary layer, which gives a very large separation bubble, creates an unstart of this intake. And this we had to change this configuration, and then we had to keep the intake little drooped so that the shock strength is reduced, and then retracting cowl and the cowl droop angle. And with this we had done an extra change the design, and this was actually thrown open in the last Sarod workshop, in which we asked all the CFD community in India to make computations for this and compare with the experimental results. In fact, 15 institutions participated. And this is the reusable launch vehicle technology demonstrator, hypersonic aerothermodynamics, evaluation of automated navigation control, and thermal protection. So these are the things which are going to do. And we had 3 landing missions, and I am going to show one of them here. And this is the hypersonic entry conditions. You can see here, in the suppose in a hypersonic flow, when it re-enters at very high Mach number, something like Mach number 20 or so, you can see here, if you are seen this as a perfect gas, that is, there is no reaction taking place. You can see the shock standoff distance is much larger, whereas in the reaction case, the shock is much smaller. It's very closer to the body. This is because when the oxygen gets dissociated, it becomes cooler. And when it's a cool gas, you can push more mass flow through this limited smaller stream tube, and that is why you have a shock standoff distance coming together. And so these are the various phases: hypersonic phase, the thermal and area management phase, and the approach and landing phase. This particular phase, we have already done 3 tests, and we are going to see. And these are some of the aerodynamic heating studies done on the wall catalytic effect. That is, assuming the wall is fully catalytic and non-catalytic, which means that the oxygen that is coming there can recombine at the wall and giving a lot of heat of dissociation onto the wall. And so, these are the aspects of this, and these are the various studies that are done here, and how with the thrusters which are there to control this, how does it affect the flow field. All these things are there, and the gap flow through these elements also. These are all the studies that are being done. And you can just click here, and there will be can you just click here? There's the autonomous landing of that. Yeah. So this was done in 23rd June, and you can see here it was dropped from a helicopter at around 3.5 kilometers. And we had also seeded it with, so that you can be able to see the base flow. and it lands at a very large speed of 90 meters per second. So that is quite a challenge, and this landing gear design was actually done by a private company for time to. So it's completely autonomous landing. So this phase of the mission which we have already carried out. The big parachute, yeah. Well, these are the technologies for vertical takeoff and landing which you are going to do. One is the supersonic retro propulsion, which is the challenge in the deep throttling of this. You should be able to control the thrust so that you can land back safely with a booster like what you do in SpaceX. And the landing legs, the grid fins, these are some of the things. And we also have a project for this vertical takeoff and vertical landing using this test vehicle. So this test vehicle will do multiple things. We do vertical takeoff and landing, we do cruise escape system, we also do the hypersonic air breathing engines also. So all these things in one vehicle which they are doing so that to optimize the cost. And these are some of the softwares you have developed. This is the Pravaha software which I am personally involved on the CFD side, and this is on the final element answer structures called FEAST. We had very recently done this one in IIT Hyderabad. These also both are in-house developed because we thought that we should not work with black boxes, but we should also know what's really happening inside the code. And these are some of the results with the other softwares like Crew and CFD++ and Pravaha. And it's showing good results. And this is some of the features of this code. I'm not getting into details. Of course, it's also parallelized on a cluster of machines. It can just on several thousands of course it can do the machines, and we regularly do millions of cells calculation in matter of overnight simulations. So these are the things. It's a RAN CFD solver. It has all this stuff of the whatever CFD things is capable of doing it. Language C++. And this is on the another code which also I have been personally. It's a Paras 3D code, which is a Cartesian mesh based code. It's like a NASA's Cart 3D. And so this is developed in C using CUDA and NPI, and it's multi-grid CPU versions. I'm not getting the details, and this is the adaptation that is done there. It's multi-grid adaptation, and this is all done using the GPU. So GPUs has a special architecture called SIMD architecture, the single instruction multiple data. So we had to group these cells into different groups and then do the computations. This is one group, partial cell one group, air cell one group, neighbor split one group, neighbor split one group. So you can do group-wise computation so that you will be the GPU, otherwise GPU performance will be very, very poor. And we had done a lot of work on this. Well, this is the sample return missions from Moon and Mars, which we are going to do in future. And landing by parachutes. The orbiting satellites, LEO is up to 2000, GSO is 36,000. Space station, we are going to have 400 kilometers. We are going to have a Bharati Antariksha Space Station by 2028 is the first module. By 2035 it will be operational. And we are also going to have in Moon and Mars landing, which is going to be a thin atmospheres. So studies are already on. In fact, government has already cleared these missions to Venus also. And these are already I told sustained human presence we are going to have. These are the various immediate, short term, medium term, and long term. These are the things we are doing. So this is what we are going to in between 2025, 2035. These are the things which are doing: long duration docking and EVA, bio-regenerative VCLS, a supersonic parachute, emergency proactive, all meteoroid impact testing facilities. And this is for the medium term from this, and these are the long term, next generation launch vehicles, and things like that. So this is going to be my last slide. So this is the Space Mission 2047. We have Bharati Antariksha Station by 2035, first module by 2028. Lunar sample return by 2030, lunar exploration, soft landing on Mars, Indian moon landing by 2040, and Venus atmosphere studies. These are all going to happen. And so with this, I thank you for giving me the opportunity. Yes, seeing so. So now I'm open to questions. Yes.
So, according to mission perspective, for humanoid missions, which is more safer, reusable vehicle or the capsule re-entry?
No, see, reusable vehicle, that is like space shuttle you are telling. See,
Yes,
the space shuttle, that one, that space shuttle is already now grounded.
Yes,
because there is no escape system there. So currently, if you say the conventional capsule system is more safer unless you have an escape system also in that. And if you are doing a re-entry that is like space shuttle, instead of having tiles, you should have something like the metallic TPS. So that's there, the material technology and things like that will come into picture instead of the conventional tiles, because tiles can break and it come out. So one tile goes also, it will be a failure. So unless you have, because in human rated vehicle, you should have always option for escape, which is there in the present mission. And the current thing which you are talking about, reusable launch vehicle technology demonstrate, is not a human rated one. Yes. But we are going to make it human rated much later. Yeah.
So then for assembling the space station in space, so are you going to send astronauts by?
No, astronauts will be there. That capability will be there. That's why already we have plans for that. In fact, one of the astronauts is now going to go to ISS and it's already there. Shukla or so that will be there. But then we also are going to have docking in space. Docking this automatic this one. So that's what we have done very recently on the space docking experiment. So that has to be perfected. And so we will be doing basically the assembly is by docking. Okay. Both manned as well as unmanned, both will be there.
Yes.
Sir, what are the economical and strategical benefits of the Gaganyaan mission for India?
Okay.
And how do you measure its success?
Yeah. So this. One thing is, if you say the economical benefits, there are a lot of other side benefits of that, because you do a lot of technology developments. In fact, in NASA itself, there are several of the offshoots of that has benefited in many other industries. Okay. And the second thing is always strength respects strength. If you want to attract many investments coming, you should be a very technology advanced nation. Why everybody is investing in USA? Because it's a technology advanced nation. So we should be also, in part of that, so that we can attract a lot of other intangible benefits will be coming. If you really measure what is you are going to get from that, other than the side benefits, the side economic benefits are much larger as compared to the tangible things which you really are trying to measure.
Good evening, sir. My question is, are there any sustainable end-of-life disposal strategies for spent rocket stages in LEO orbit and beyond?
Yeah, it's a good question. So it is there. So now what we have done is, now all these orbits, we are trying to see that once we put the satellite in the low Earth orbit, we are deorbiting it and then bringing it to down something like less than 350 kilometers. In fact, I was just suggesting that all our fourth stage of PSLV is becoming polar orbital experimental mission. And VAT can also suggest a satellite, a small satellite. In fact, last time we flew something like 35 with various startups and various institutes. They have all done it. So why not VAT also? So you can just propose and then you can contact in space and they will be prepared to put your satellite, and then it will be a good interface with our space agency, and you will get to know about really working with us. That is one way of interacting and getting with the ISRO agencies. So what we are doing is all the low Earth orbits we are deorbiting, we are bringing back to something like 350 kilometers orbit, so that the lifetime is around less than 2 years. And other things, the satellites which are in 600 kilometers orbit, it will be very much there. So all the spent stages we are bringing it down. But the satellites there, what we are doing, either what we are doing, we are deorbit, then you lose the light-on satellites. Whereas in the case of the geostationary orbits, there's something called the graveyard orbits. You take it to a graveyard orbit that is higher than 36,000 kilometers or lower than that, and then put there in the graveyard orbit so that it is a separate, so it doesn't clutter. But yes, this is an issue because Starlink has so many satellites, and it is still an issue of how to handle the space debris things. In fact, there are international guidelines to say that a satellite has to be only this much. So many of the things which you are doing, that's why when we are leftover propellants, we are venting it out and seeing that they don't burst the launch vehicle, and they burst the spent stages.
Hello, sir.
Yeah.
My question for you is, so what are the improvements that can be done to handle the TPS materials while re-entry of the vehicles?
See, one thing is it should be a low density material because we should be minimum as weight as possible. At the same time, it should have a very high thermal capability, in the sense that it should be able to withstand very high thermal heating. So in the case of, if we talk about typical ablative material, then what should happen is we should ablate in a low this one what do you call it? The ablation heat of ablation should be quite high so that it will the material will be able to withstand very high heating levels with very low density. If you are talking about a material which is going to be not ablative but the hot structure material, then it should be able to withstand very high temperatures, something like 2000 degrees Celsius or something like that. So the material technology is to have, if it is a hot structure, it should be able to withstand very high temperatures, which means that you should have very good coatings, like we are doing silicon carbide coatings, okay, zirconium dibromide coatings. So these are the technology which are needed, and both in the case of the ablative materials, we need to lower the density and have good ablation characteristics. In the case of the hot structures, we should be able to withstand higher temperatures. So these are the two areas.
We'll have one more question. So, good evening, sir. Thank you for covering such a huge field. Got to learn a lot. You covered RSLV, in which, in one of the first median launches, during the orbit intersection for satellite, that was off the mark because of failure of logic in the sensors. How did you come across that failure? And
which one you're telling of, PSLV?
So RSLV, there was an orbit intersection which went wrong in its maiden flight, I believe.
RSLV, PSLV, yes, the first flight was a failure.
Yes.
That is because of the logic. What happened was, there's a flight computer is there. The flight computer, what happened was, when it was exceeding the 10 volt things, the sign got changed. So there was a sign change in the this one. So the memory, there was a memory overflow which was not handled properly. So that was the condition. There was a retro failure, and because of retro failure, it called for very high, the voltage for the corrections, and that beyond a certain voltage, what happens? The sign got changed.
Inverted.
Yeah.
So it was a retro thruster failure.
No, the retro thruster failure led to this control system failure, which led to this this one.
Okay.
But
And
it was
how did you
basically a
resolve
flight computer. Then that's why there was the first failure in 1993. Then we had a separate. We formed a flight computer. There is a separate group to handle this particular thing. And now it's completely thoroughly it is validated. We do there is onboard in-loop simulation, hardware in-loop simulations. All these things are done, and there are stress cases are put. And then on the ground we do all this computation along with the actuators and with the sensors and see that the mission is going properly.
Thank you, sir.
Thank you, sir, for giving this brief description of launch vehicle and re-entry missions. Now, I would like to call upon the stage our conference chair, Dr. Prashant GK, to give a token of love and respect.
It's just opposite to that.
Tomorrow will be as per the plan. Yes, sir. Yes, sir. Yes, morning service. Service is arriving in evening. Oh, around 9 p.m.